Attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top, allumage P120, décollage. Propulseur nominal, début du basculement. Propulseur nominal. Séparation P120. Séparation biomasse.
This is wonderful news.
What an amazing achievement this is. My skin is always, and I'm always shaking with enthusiasm. And welcome to Ljubljana, welcome to Slovenia. Dobrodošli v Sloveniji. It is a great honor that ESA has chosen University of Ljubljana to be the host of this event. So I would like to thank all the people with whom we have collaborated, especially Francesco and Klaus, but the whole team. We have here today participants from every continent except Australia. This is a really big achievement. And projects like this can succeed only if we work together, if we work together as one group. And this is the result of such achievements. I hope you will enjoy the next 4 days. It's a packed schedule, and I see a lot of existing friends here in the room, but I see, and this is what I'm really, really happy, a lot of young faces, and I see a lot of new friends. So work hard and also party hard.
So thank you, Christophe. And now it's my turn on behalf of ESA to welcome you all here. Of course, not only from me, but also from Klaus and from all my colleagues. We are very happy to host here the 12th edition of this workshop. But it's the 12th edition of the Polinsar workshop, but it's also the first joint workshop with Polinsar, Biomass, and the Calval of Biomass, because now we finally launched this mission that was first proposed during the first edition of this workshop in 2003. So it's a big success. For many years, we've been waiting for this event, and actually we've been postponing this event. It should be every 2 years, but we waited until Biomass was launched. So finally, we can show first results based on this mission, and also we are hosting the course of polarimetry next week, again using partially biomass data. So it's a big achievement for us and also for you. For many years, we gave you data from third-party missions or other agencies or campaigns, and now finally we can give you full poll data acquired by ESA. So we are very happy. I have a few minutes, so I should pass a lot of information to you. So I have a few notes so that I don't forget. You know which are the high-level objectives of this workshop, which are similar to the past editions. So we have to present the advancement in the development of applications, of methods, of tools. We also have the Biomass Science Workshop and Calval meeting, which is associated. By the way, there will be some parallel sessions downstairs, but we try to minimize the parallel sessions so that you can attend everything. We will also inform you about the mission status and the phase E2 activities, present the first results on the instrument performances and the commissioning phase, and review the state of the Calval activities, and many others. So if I should recap briefly the history of Polinsar, we started in 2003, so it was more than 20 years ago, and we started in Esrin, and after many editions taking place in Esrin, we went to Toulouse in 2023, that was organized with Yves Louis, who, by the way, is there, and he's the person that followed Polinsar for many years, for decades. So welcome, Yves Louis, back here. We are very happy to have you here. And I'll show you a picture of the first edition of this Polinsar. You see many people who are still there, and some who are no longer there, but thanks to all these people and many others, the achievements of this workshop and also the achievement of this mission have been possible. You see, by the way, Thuy, I hope she's there today, and Thuy, no, she did not arrive yet, maybe. Fabio Rocca, I hope he has come as well. So really many people that were in the beginning of this conference hopefully will join this week. We have achieved during these 20 years many results in terms of polarimetry tools and applications, and we will also discuss in this edition the recommendations and the perspective for future polarimetric missions. So you will see also which is the status of preparation of mission, full pole missions like Roselle, also Sentinel-1 next generation. We have a full pole capability. And I think Clément will present all of them. It's also interesting to hear about the Harmony Earth Explorer that has been approved, which will also allow some form of compact pole equivalent, also very interesting. And many scientific results. By the way, you will see the MAP platform that now is operational, which is a joint ESA-NASA platform where the biomass data can be accessed and processed together with NISA and JEDI. And this will be used also for the training course next week, by the way. During these many years, we developed more and more the associated tool for polarimetric processing, Polinsar Pro, which is now completed. So the contract is closed, finally closed with Eric. This can be downloaded still from the University of Rennes, but we started the development in Python following the recommendation of this community. So now the first routines are available. They are being transferred to MAP. And more and more will develop routines in Python. We have to decide also with you whether we want to continue to keep the C version or rather develop all the tools in Python. But these are all things to be discussed during the conference, and we will collect more recommendations from you, and we'll discuss also the status of the past recommendations. Magda will do that today. We should remember also, well, we have invited guests that I mentioned before. Many of them will attend today or will come later. And I would like also to remember one colleague that unfortunately passed away last year, Pascal Dubois. She contributed a lot to the achievements of this community. And all of us, including her ONERA colleagues, remember her and miss her a lot. So this should be all. I would like to mention that Slovenia is the latest new member state of ESA, so it's one more reason why we are hosting this conference here. We are very grateful to the ministry and to university for giving us the facilities to host this conference and the course as well. And by the way, there have been already 2 training courses on remote sensing in Slovenia. There was the land training course, I think was last year, before. And then we had also a course in Maribor that I organized many years ago about remote sensing, radar and optical remote sensing. And it will be the third ESA course that will be next week about polarimetry. We know that there is not a strong tradition in radar polarimetry in Slovenia, but that's also a reason why we want to do the course here, to increase the know-how in this new domain. And I hope that this conference, that this course will encourage students and scientists to get into this domain and contribute to this community. So now I will hand over to the next speaker, which is Mateusz Frangeș, the State Secretary of the Ministry of Economy. And welcome, Mateusz.
Welcome to Slovenia. I don't know if you're aware, but Slovenia is the only country in the world that has the word love in its name. And it's not a coincidence, because everything we do, every relation we create, the way we innovate or the way we host our guests, we do it with love. You will find a Slovenian hospitality these days, and I hope you'll enjoy it. Maybe a small anecdote. I'm not sure if you're aware, but on the list of the most desired embassies of the Federal Republic of Germany is Ljubljana. There is a long list of candidates from, all diplomatic backgrounds that would like to be an ambassador of Germany in Slovenia. Do you know why? No big open problems, high quality of life, great economic base, top-notch science and innovation, and a great desire of national economy to transform. We believe that we live in the times of biggest economic changes the world has ever seen, driven with geopolitical, technological, climate change, cultural and social drivers, and we want to use those changes, not as a threat, not as a danger, but as an accelerator to transform our economy into the next European hub for innovation of advanced and sustainable technologies. And sustainable technologies are the ones that are already at home in Slovenia, because our love also reflects in our relation with nature. Slovenia is the third among European countries to be the most forested one. So imagine Sweden and Finland, right? Nordic countries. And it's cold out there, right? And we are the third. More than 60% of this small territory of Slovenia is proclaimed as the Nature 2000 protected areas. We have great quality water reserves. However, on the other hand, we know that we might be one of the most affected areas in the world because of climate change. With great tradition in our forest industry, in preservation of woods, of our biodiversity, and a very progressive country advocating the necessary measures to combat the climate change, Slovenia is really proud to host this conference. Yes, on January 1st last year, 2025, we've realized our ambition to become a full member of European Space Agency. In European space programs, 3 Slovenian universities, more than 50 companies are already engaged, and they prove themselves in great science, innovation, technology driven sectors and solutions. For example, Slovenian company called Synergy. Synergize, sorry. And I heard that something is missing. Developed a democratic access of humans to space with their technology called Sentinel Hub and Copernicus browser. Actually, they revolutionize the access of researchers, businesses, societies to access the data we collect in space in various Earth observation programs. And yes, a part of being a culinary and wine superpower, we're also a superpowered in Earth observation programs. And it all starts with people. Thank you, Professor Oštir, for bringing this conference together with Francesco and Klaus to Slovenia, but also thank you for your dedication to the topics you evolve not only on such conferences, but also as a Slovenian representative in expert committees covering these programs. So, our national campaign, when we shared the aspiration to join full membership of European Space Agency, was driven by a very simple motto. Slovenia may be small on Earth, but we want to be big in space. We are going there because we seek solutions to improve life. We don't want to have an emergency exit to Mars. We know that we are sending our technologies and our experts in space in order to find better knowledge, better solutions to improve the life on Earth. Again, share the love, the world needs it, and I hope you'll have a remarkable time in Slovenia. And remember, from all continents you're coming from, all the guests are very welcome in Slovenia. Thank you.
Thank you very much, Mr. State Secretary, for those kind words. And our next speaker is the Vice Rector of the University of Ljubljana, Professor Gregor Dolinar. Please.
So, distinguished State Secretary Matej Frangaš, esteemed colleagues, delegates, welcome to Ljubljana, welcome to this conference. On behalf of the University of Ljubljana, it's my great pleasure to welcome researchers, professionals, and students who have joined us from all around the world. It's a true honor to host you here in Ljubljana, and I'm proud to open this important gathering dedicated to understanding one of the Earth's most valuable and complex ecosystems, our forests. So this event is hosted by European Space Agency in cooperation with the University of Ljubljana, Faculty of Civil and Geodetic Engineering, and Slovenian Space Office. We are proud that Ljubljana has become a meeting point for a cutting-edge Earth observation science and a community shaping the future of forest monitoring and climate research. Forests are essential for life on Earth. They regulate climate, protect biodiversity, sustain livelihoods, and play a central role in the global carbon cycle. Yet forests are increasingly affected by climate change, natural disturbances, and human activity. Understanding forest structure, biomass, and long-term dynamic is not only a scientific challenge, but also a responsibility we all share. We already heard that Slovenia is supposed to be the third most forested country in Europe. I checked, of course, with AI, and it was a nice list. So the first was, Finland, then Sweden. Then it was written Slovenia, and after that Montenegro. But the percentage of forest in Montenegro is a little bigger than in Slovenia. So this is another proof why we should check everything what AI is telling to us. So at this moment, it's not completely clear whether we are the third or the fourth, but basically the difference is a minor one. Anyway, forests are really important for us. They are part of our culture. They are part of our identity. Not in many countries, but in some countries, you are not free to walk in the forest. In Slovenia, this is the case. You can walk everywhere in the forest, and that means we can walk freely in 2/3 of our country. That's something we really appreciate. So these forests are important for economy, and of course they are also part of our heritage, and we are very proud of that. This week we will follow the progress of ESA Biomass mission, part of the Earth Explorer program, and explore how advanced radar technologies, especially polarimetric and interferometrics, are transforming our ability to observe forests with unprecedented accuracy. These methods enable us to look beyond what is visible from the ground and more accurately quantifying forest structure and carbon storage from space, supporting climate science and evidence-based policies. I'm very pleased that here the people from many different organizations gather. And here there are researchers, policymakers, NGO representatives, students, commercial stakeholders. This diversity reflects the growing importance of Earth observation, not only in academic research, but also in practical decision-making, environmental management, and sustainable development. It also reminds us that progress happens most effectively when science, public institutions, and industry work together. At the University of Ljubljana, we strongly believe that scientific excellence must go hand in hand with education and talent development. The future of Earth observation depends not only on advanced missions and technology, but also on skilled professionals who can interpret data, develop methods, and apply results meaningfully. That is why we place great importance on educating the next generation in geoinformatics, Earth observation, and artificial intelligence. In this spirit, we are proud to play an active role in this ESA Earth Observation Training Academy, which will happen after this conference. Let me finish by underlining a simple truth. Forests matters, ecologically, economically, and culturally. With this ESA Biomass mission and the collective expertise and commitment gathered here this week, we are better equipped than ever to understand forests and safeguard them. So with this, I would like to welcome you again, thank the organizers, and I wish you a very nice weekend here in Ljubljana, and I hope it won't be foggy all these days. Thank you.
I can introduce myself, yes. Good morning. So my name is Klaus Cipal. I'm co-hosting this workshop with Francesco and Christoph. So my task is very briefly to talk you through the logistics of this workshop, so I will not take too much time. Next slide. It was already mentioned, so we have combined in this conference actually 3 different workshops. So we have the Polinsar, the classical Polinsar workshop, which we already combined in the last years with the Biomass workshop. And of course, since we launched the mission, we have also the Biomass Calvary workshop that we usually have every year. And we combined this as well with this Polinsar conference. So this led to a bit of a packed schedule. We will start today with the general overview sessions, so SAR missions, Polinsar methods. Tomorrow we will focus a bit more on biomass. It will be biomass, a general overview from ESA on the status of the mission, and then first results. And I really expect a firework from all of you. I've seen some first images and it's really exciting. Tomorrow on Tuesday we also have the poster session. So there's a poster session there's a poster area downstairs and upstairs. You can put the poster up already today. You can keep it through the full week. You can view the posters during the coffee breaks. And we will also have drinks tomorrow at the poster session. As we have a packed program, a lot of talks that have been suggested as oral talks had to go to the posters, so it's really exciting. There's a lot of exciting results, a lot of exciting ideas, so take the time and visit the posters. Wednesday we continue with first results from biomass, and then we will split. So we tried to avoid a bit parallel sessions, but it was not possible to entirely do that. So we have the land applications on Wednesday afternoon, and in parallel the biomass campaigns. So it's very specific biomass-related campaigns and ecosystem modeling that is really linked to the biomass mission. And that will be in the downstairs room. It's in the purple room. You cannot miss it. It has a purple door, so it's easy to find. And then on Thursday, we continue with the general overview, Polinsar campaigns, geology application, cryosphere application, ocean applications. And keep in mind, there's a lot of biomass talks also there, so biomass doesn't stop after Wednesday. There were a lot of first results also over deserts, over ice sheets, and that will be presented in these sessions. And on Friday, we have the Tomosar session, and at the end, the recommendation. This reminds me, for all the session chairs, please take notes of recommendations. We take them very serious. Magda will present afterwards the recommendations from the last years and the actions we were taken. So if you have any idea, if you have any wish to ESA, if there's any discussions where you feel this is of general interest, take a note and let us know. I think we will also set up a Padlet that you can fill this in online. For the coffee breaks, logistics, no, presentation upload. Here's the Regia. You can upload it here or with Sabrina, sorry. Downstairs, there's also a Regia where you can, in the back of the room, where you can upload your presentations before the session starts. What else do I have to say here? Conference, I think I've covered all of that. Huh? Icebreaker, I'm coming to that later, so I think that's fine. Next. Social events. Christoph mentioned it before. Polinsar was always not only a place of having nice science, it was also a gathering of a very nice group of friends, and social events were always very important. So there is four social events that we planned. Today at night we have the icebreaker, immediately after the conference. Tomorrow we have the biomass party. So there was actually one of the recommendations of the last workshop, and that you see we take our recommendations very seriously. I think it was Felipe, I don't know if he's in the room. We organized at Toulouse the first Polinsar party, and we repeat this here. So we will meet tomorrow at Sorica. It's very close, it's 50 minutes walk. You have it here on the map in the northwestern part. You can walk there. Drinks are on ESA, at least until the budget is gone. So the first drinks are on ESA. Make sure you eat before. You will not be served food there. So we meet there at 8. You have some time to grab some food before you go there. Also very important, it's not only party hard, it's working hard. So we expect everyone to be back on Wednesday at 9 o'clock sharp here. So there's no excuse. On Wednesday, we thought, because we are in a very beautiful, not only beautiful country, in a very beautiful town of Ljubljana. It's a very nice old town. So we organized guided city walks, which will be immediately after the meeting, after the conference. If you have not registered for those, go down to the girls, to the reception desk, and talk to them. I think there are still free spots that you can take, and we can try to fit you in there. The weather should be awful on Wednesday. I checked, it should be rain like hell, but we brought some umbrellas, so you can still enjoy that. And because we are not only in a very beautiful town, we have also very warm hosts. They kindly invited us for a conference dinner that is sponsored by the ministry. Thank you for that. So on Thursday, we will have a joint dinner with all together, and I'm really warmly welcoming you there, and I hope you can all make it there and we have a good time there. So that is the social aspect of the conference, very important. One more thing, so there's 3 more things I have to mention. On your desk you find a QR code. We have started a survey to support or to improve our data access and tools. So there is often some complaints that accessing to ESA data is not that easy. Don't complain, help us to improve it. It takes 3 minutes to fill out this survey, this questionnaire, and it really helps us to improve our data access. We will send you an email. I think we have already sent an email before. We will send a reminder after the conference, and there you can, if you have any wishes, any criticism, put it there, help us to improve. Then, second thing to help us improve is, for Biomass, we go a new way to provide data access, and that's the ESA map. That is new, and many of you might have started to work with it as Biomass data became available. You might have experienced some problems with it or not. As I said, it's a new thing. We do this for the first time, so naturally there might be things that work very well. There's other things that might not work so well. Take the opportunity here. We have Roberto Alacevic here, who is running this map activity. He has a desk downstairs in the poster area where he can help you solving issues and helping you accessing the map. If you experience some problems, don't start yourself getting frustrated with the thing. Go downstairs, visit Roberto, and he can help you. There's also a presentation on Wednesday, I think it's on Wednesday or Thursday, Wednesday, where we can show you a bit more details on the map. There's also downstairs a desk, by the way, for Polinsar Pro. Olivier will sit there for the Polinsar Pro software, where you can make your recommendations how to further improve the tools. One thing, you see a lot of other colleagues here. As I said at the beginning, we combined, or we also host the Biomass Calval workshop here. Biomass Calval workshops, or Calval workshops, are very specific workshops where we discuss mission-specific items, but not only science, also technical things like access of data, access of tools, and those sort of things. We didn't have the space to fill it into the program here. So use the opportunity. If you have any question, if you have any problem, talk to one of the guys down here, and they will help you to solve your issues. They will take your recommendations. If you have any wish that we should improve, or where you need tools, or where you need help, talk to one of these people. We have Björn, our mission scientist. Cristiano is our ground segment manager. Clément is responsible for the sensor evolution, the algorithm evolution, and Calval activities. We have Muriel, who was running the implementation of the Biomass processor, and myself. Grab us during the coffee breaks or during the social events. Talk to us if you have any issues. This brings me to the end, and I just wanted to make you aware of one thing that we received a call a few days ago, two weeks ago, that we were awarded an award, an ASTRO award. I have to say, before I got this call, I didn't know about the ASTRO award. It was new to me. So it's the Everyday Astronaut Society. It's a society of space enthusiasts. Mainly they are launching launchers, satellite launchers, rockets, astronaut people from the US mainly. And they awarded Biomass for being one of the most inspirational, innovative, and important mission of 2024. It might not be the biggest scientific, thank you. It might not be the biggest scientific award, as I said. I mean, I don't know if you've heard of this before, but I think it's still special. 2025 was an extremely busy year. There were a lot of missions launched, also rockets, also astronaut projects that were going up. And still they decided for a European mission. It's a US society. They decided for a European mission. They decided for Biomass to be one of the most inspirational projects, space project of 2025. And these are laymen, so these are space enthusiasts. These are not SAR specialists. So they really, and I think this is really an award that shows us how satellites can inspire society and can really make a difference and make a contribution to science and to society. So I just want to share this because I think this was a very nice first achievement after 6 months in space, getting the first prize. And with this, I would like to stop and I would like to hand over to Magda is next, right?
So Maddalena will now present the main achievements since Polinsar 2023. And by the way, I want to thank Maddalena because she's behind the scenes, but she's the main person together with Sabrina organizing all the logistic and the conference, speakers, papers. So they are doing a fantastic job. And thanks a lot again.
Thank you. Okay. So before we dive into this exciting program of Polinsar and Biomass Workshop 2026, I would like to show you some of the achievements since 2023 and to show you also that we are addressing recommendations given by the community. I have the, okay, here. So I would like to show you some of the actions that we have taken since last Polinsar, but also some of the actions that are continuing since Polinsar 2021. So first recommendation that we got, so basically main recommendations that we got last time, recommendations not to the community but to ESA, were regarding the biomass mission. So one of the recommendations, the first recommendation was to investigate, for ESA to investigate to what extent the different westward drifts used during the biomass antenna pattern characterization phase and the spacecraft repositioning following the major cycle completion can still be exploited for interferometry for high latitudes. So as you probably know, baselines during the COM phase were much larger than during the tomographic and interferometric phase. So we took advantage of the COM phase 2 and maximized the number of acquisitions over Antarctica for the community to support the biomass cryosphere research. As you see here, there is a graphic showing the coverage of the acquisitions during the COM phase. Second recommendation was to consider data from commercial providers for biomass validation. So here we had a lot of discussions, and some of the discussions with the ecological teams, we agreed that we will only consider for now data of the highest standards, so repeated observations following established protocols curated by one of the established networks. For more details, you can also refer to the talk that will be in the biomass campaign session on Wednesday, the Geotrees talk. However, of course, validation using other sources by members of the community, and reporting to biomass science and validation workshops is highly encouraged. Third recommendation was to provide accurate information on the data access and dissemination of all biomass data. Of course, once the data is available, so we are now in this phase because since 12th of December, the data is publicly available. I put here a link, but in general, if you go to earth.esa.int, you can find there all details about the data collections, biomass data collections, and when you select the data collection that you are interested in, you have all the documentation on how and all the instructions how to access the data, starting from the setup of EOS sign-in account, and how you can browse the data, visualize, and process. So here we have, for the data access, for data exploitation and exploration, first of all, your interface would be the ESA Map Explorer, where you can browse the data using various filters. You can download the data there, but there is also PAL, so the Product Algorithm Laboratory, which is basically processing environment and coding environment where you can experiment with the data. For more details on MAP and on PAL, you can refer to the presentations in the Biomass First Results 4 session that will be on Wednesday morning. The next recommendation was to prepare activities to allow integration of a priori forest height estimates into the biomass AGB retrieval. So this recommendation for now is pending. We don't have any dedicated activity planned yet because we basically need to wait a bit until the products are stable and validated. But you are again invited to start investigating on this topic and report in the next biomass science and validation workshops. There is also opportunity, I will mention it also later, there will be also other opportunities to propose such activities in the Biomass Open Science calls. Next recommendation was that we should, so if JEDI AGB is used for training, we should develop our own product to better understand and control biases and uncertainties. And in the long term, JEDI should be replaced or complemented by Biomass Tomosar or Polinsar data. This recommendation as well is pending because of the time constraints. We didn't follow up on this recommendation. However, we suggest to evaluate, what we suggest now is to evaluate existing products first, and based on the analysis of these products, set up a roadmap on how JEDI can be possibly replaced in the future. There will be a small activity within a bigger project that we have, the Biomass Data Innovation and Science Cluster, that has already been kicked off. Then the next recommendation was to improve the usability of BioPal and to make it really open to newcomers, service providers who don't have expert knowledge, and for ESA to consider to organize dedicated BioPal training sessions. Here I also put a link to this collaborative environment documentation. You have the ESA MAP knowledge base where you have all the introduction to PAL, all the tips how to start with PAL and what to do, how to start experimenting coding on PAL. We also will have some people, as Klaus mentioned, in the demo desk in the ground floor, so you can also approach them. Regarding training, it's not dedicated BioPal training, but we will have next week polarimetry training, and we will also use MAP and PAL during the training. So this, let's say we took also this action. Another recommendation, ESA campaign the data should come in a standardized format concerning data and metadata with clear definitions of the level of processing. So there was an effort already made to standardize products coming from SAR campaigns. And now we added requirements to all ESA campaign contracts, and it includes provision of analysis-ready data products. 2 more, I think, or 3 more. New campaigns to explore biostatic data and multitemporal acquisitions. Here we address this recommendation for the multitemporal acquisitions that we can mention here the acquisition of AfriStar campaign series. So the AfriStar 3 campaign repeated the observation of AfriStar 1 and 2 campaigns using the exactly same sites and flight geometries. And there will be a presentation this week, so you can refer also to this presentation. In addition, we are planning a revision of a Tropistar campaign in French Guiana in 2027. And regarding multistatic SAR, we collected some data during the Tomosense campaign over the forest in Germany with the bistatic L C-band and monostatic P-band acquisitions, and all campaigns are complemented with the laser scanning data. Now, another recommendation was regarding the future studies, dedicated studies for retrieval of forest parameters, but not only. So here, unfortunately, now the call is already closed, but it was open in June. It was a fixed call for proposal, biomass plus innovation. It was a call for innovative studies, starting from methods, polarimetric methods, to biomass, forest retrievals, and so on. We received more than 40 proposals, and we will fund up to 6, maybe 8 studies, we will see, for the duration of 18 months, and the target budget per project is around 200K. And now we are in the evaluation phase, but this is not the end, because in the future these calls will be launched again. So if you missed your opportunity, don't worry, there will be another opportunity. Then there was a recommendation to introduce a session on biostatic polarimetry in support of harmony. In this conference, we don't have it, but this is also for me occasion to advertise our next conference that may be interesting also for this community. Fringe in 2026 in June in Krakow. We will have, or we are, at least the intention now is to have a session on biostatic and multistatic SAR. Now still the abstract submission is open until end of February, so if you want to propose something, it's still there. And then 2 last things. These are actions from Polinsar, actually Polinsar 2021, but maybe this recommendation was a 20-year-old recommendation from the community, a very persistent recommendation, to establish or to create an open multi-frequency fully parametric SAR reference data set. So this was started, we started to work on it in 2024, so after the 2023 Polinsar. We established an activity, Pulsar activity within a CEOS LSI VC working group, and Ake will have a presentation in the first session, so in a while. The main milestones in 2025, we defined the Pulsar science team and reference sites. We compiled the observation request for each of the contributing SAR missions. And now we are going to coordinate observation tasking with the agencies. For now, we have 26 reference sites, which are covering a variety of locations and land cover types. So, but more Ake will mention later on. And finally, the last one, but not the least one, the recommendation from 2021 regarding tools for processing polarimetric data. So today I can say that finally, not finally, but after 20 years, we completed development of Pulsar Pro. More than 20 years of development and maintenance. This project is now closed. The software is, of course, there. You can still download it. It will not be maintained as it was before for the next years, at least. Unless there is another recommendation from the community, we can always adapt to this. The software is, you can download it from the step.isa.int. But in the meantime, we started another activity, which was the re-implementation of selected Pulsar Pro functions in Python. We even have now a logo. Thanks, Olivier, for a super logo of Pulsar Pro. Olivier will present in a while, and he will be also present in the demo desk downstairs. You can find him there. So we re-implemented, of course, not full Pulsar Pro, but we have already a lot of functionalities. The source code, everything is on GitHub, everything is publicly available. There is a lot of documentation, tutorials, a lot of materials. Together with Olivier, there is Armando Marino, that I'm sure everybody knows, who is also our scientific advisor, who is making sure that the results that we get with this new software are in line with the original Pulsar Pro. So our quality manager. And now the last activity, maybe since a couple of days or weeks, we started integration of the code on MAP. So it will be also available for people working with the biomass data. You will be able to use the code. So this is the last recommendation. So as you see, we take it seriously. That's why we really invite you, all the chairs, all the community, to provide recommendations during the conference. And then, as Francesco mentioned, at the end of the conference on Friday, we will have dedicated sessions. So please keep in mind all the recommendations and ideas if you have for Friday and share it with us. Thank you.
Thanks, Magdalena. With this, we are closing the opening session, and we are moving immediately to the first working session, and I invite Irena and Francesco to chair this session.
Name tag, yeah. Not a problem.
So, good. We'll start this new session about SAR missions and Polinsar initiatives. The first talk will be by my colleague Clément Albinet, working the ESA ground segment in charge of data quality, among other things. And thanks for changing the name. Irena Heinzecke from ETH and DLR is co-chairing with me. So Clément will present the status of SAR missions and also perspectives for future missions.
Thank you, Francesco. Hello, everybody. I have only 20 minutes to present all the SAR missions of ESA, so it's a little bit challenging. I will try to go to the main points. So here you can see that ESA has been working on a lot of missions, 85 missions. And among all these missions, a lot of them are SAR missions. I will try to address all of them. As you see, it's a really big number. The first one is Sentinel-1. Most of you must know it. The mission, SAR mission has the highest number of users. In terms of health, we have Sentinel-1A and Sentinel-1C flying, delivering data. Everything is working very, very well. On Sentinel-1C, we could see a little, let's say, degradation of some transmit-receive modules. You can see on the left. It's not dramatic. We're compensating it. And it's a little bit the disease of all the Sentinel-1 of that type of issues. You can see on the right, we also had a TRM failure on Sentinel-1A since a long time. And that's not having a big impact. If you work with Sentinel-1A data, you must have seen that we had the degradation of the baseline, INSAR baseline, with larger INSAR baseline because we have issues with the thruster that are degrading. So to make an economy of this thruster, we are not maintaining the orbit as well as we should. So you can see on the right, on the top right, you will have larger baseline according to the latitude. What is a problem for some users can be a benefit or good things for others. You will have larger baseline with Sentinel-1A. And we don't have this issue with Sentinel-1C, and we'll not have this issue with Sentinel-1D. So when we operate Sentinel-1D, things will go back to normal. It's not only impacting the baseline, it's also impacting the burst synchronization. You can see on the bottom left here, bottom, the larger baseline, and the top left, how it's increasing the burst synchronization. So here's also a small issue that will be only solved when we work with Sentinel-1D in a few months. Instead, in terms of radiometry, we have following the calibration with the absolute reference target and the rainforest for the antenna pattern. You can see on the bottom left that we have a radiometric accuracy derived from point target of 0.3 dB, 1 sigma, so it's extremely good. It's below the requirements, so we're very happy. We improved recently this EIP estimation using different river mask. We use a wetland mask derived from ALOS So we can see that even if we're working on Sentinel-1, we're using other missions data. I mean, it's very interesting to use the best of what you can have. And on the bottom right, you can see that it's improving a lot, this measurement of the elevation antenna part, and allow with less data to have better statistical value. Maybe you have seen that a few years ago, from July 2023, we're generating this ETAT product. So it's an additional product containing timing layer, that allows to improve the geolocation accuracy of the Sentinel-1 data. You have a tropospheric path delay, ionospheric path delay, solid Earth tides, and correction from the Sentinel-1 system. We didn't want it to update the Sentinel-1 data, not to break the time series, so we provide it as additional layers. And it allows to reach, you see in range, a geolocation accuracy of almost 20 centimeters, which is excellent, and in azimuth, a couple of meters. This product was updated since June last year. We added additional layers, tropospheric delay gradient, and the ocean tide load correction in range and azimuth. And thanks to these additional layers, we can see, you see on the top without the ocean tide load and the bottom with the ocean tide load, you improve a lot the measurement of the deformation. Here it's in Brittany, inverted, if we, my comment on that. It's inverted, but it's Brittany, and you can really see that you are not impacted anymore by the ocean tide load. In terms of orbits, in the past we're having only 3 orbits delivered. We added a 4th one, which was a recommendation from Fringe in 2023. These are the medium accuracy orbit ephemeris. And if you can see, it's almost the precision of the precise orbits, but we have them in 30 hours instead of 21 days. So it's really fulfill a lot of use case that can accommodate with 30 hours, but need still a precise orbit. In general, if you want some information about the performances of the Sentinel-1 sensors, you can go on the ESA website, you can look for it. You have the quality disclaimer that all the issues, if there is an issue with one image or any data, they're all reported there. All the quick look are inspected, all the data is inspected, so everything is reported there. And you have more general report on the top right. Big thing that happened in November last year is that we launched Sentinel-1D. It was a very successful launch. The satellite was an extremely good orbit that allowed to save some fuel. We're very, very, very happy. It was launched in the 4th of November. We had very recently, the first image that was published. It's still work in progress. I cannot share much more information because the commissioning phase is not over. It's planned to be over in April, in a few months. And Sentinel-1A will be decommissioned after that. So we'll go back to configuration always of only 2 satellites, with, in this case, good orbital tubes. In the longer future, you see Sentinel-1C, 1D in around 2034. Will need a continuation. Space mission needs decades to be put in place. So we already started to work for a while already on Sentinel-1 next generation. That should be 2 units, should take over Sentinel-1D and 1C. And we gather user needs from the European Commission, from different expert groups for the mission requirement documents. And you can see on the right that it will fulfill all the needs, some needs of the Copernicus services, and also enhance them. So the idea is to take over the current C-band SAR data production, but to improve it also, to allow additional use case. So to summarize, it will allow to enable new applications like soil moisture, small ship detection, ocean current. You will have higher resolution, thinner resolution, 25 meters square. We have 100 meters square per pixel today with Sentinel-1. Better sensitivity, shorter revisit time. The swath will be larger, combined with other missions, and quad-pole capabilities that will be used more certainly over some small areas, that it will be the case for Roselle and NISAR. And there will be a higher duty cycle and dedicated the North Polar mode, so there will be more data and better data. And currently it's in phase B1 development, so the satellite should start being built this year. Here you can see comparison in terms of numbers. I put in red the differences. You can see the main differences are the coverage from minus 80 to plus 90 degrees with polar mode, so we'll cover completely all the poles, the North Pole. The swath will be in minimum 400 kilometers, which is the case of the EW today, but not the case of the IW. Resolution better, noise equivalent sigma naught better, quad-pole capabilities, and the possibility to do a long track interferometry. And with a duty cycle, that would be a 43 minutes per orbit, which is a lot, up to 53 minutes. So it's really, really big number, even compared to Sentinel-1, which is usually in a good situation. For biomass, I will not talk too much about the mission because, as Klaus presented, we'll have 2 full days for the mission, so I will not say anything more. I will let people present it. I will go to Harmony. Some of you might already know the mission. It's the 10 Earth Explorer mission. The objectives are very diverse: upper ocean, ocean-atmosphere interaction, land ice and sea ice, and tectonic strains and volcanic process. It's 2 satellites, a companion satellite to Sentinel-1, with SAR instrument and thermal infrared instruments. They will fly in bistatic configuration with Sentinel-1A. The launch is estimated to be in end of 2029, so in a little bit more than 3 years, which will come very, very fast. You can see that there will be 2 configurations on the right, a cross-track configuration that will be used for the first year and the 5th year of the mission, and a stereo phase with satellite before and after that will be during the 3 years in the middle of the mission. This is the base. As all Earth Explorer, it could last a little bit longer. It depends also on when it will be launched and the life of the Sentinel-1 first generation. Roselle, it's L-band SAR mission. It's planned to be launched in around 2930 here. The idea is to make some gap filling and to enhance the continuity with Sentinel-1, so it's not only L-band SAR data, but it's also more data. With Sentinel-1, in terms of requirement, here is for next generation, we can see that there are some use cases that will be supported by the L-band that are not supported by the C-band. So it will enhance, increase also the number of applications, what can be done. In terms of satellite, it will be here again 2 satellites that will fly. The orbits are the same as Sentinel-1, so there will be 6 days. So global, 3 days over Europe, every day over Arctic, repeat cycle of 6 days with 2 satellites. L-band, it's 85 megahertz bandwidth, a lot at 1.2 gigahertz. And it will really fly in synergy with Sentinel-1. Currently, we're in phase D, and the reception of satellites should be in 29, so for a launch expected in 2030. In terms of modes, they are inspired by Sentinel-1, so we call them Roselle interferometric mode, but it's the requirements are coming from Sentinel-1, IW, and you see on the extra wireless mode EW, so the swath is around to be the same. The pixels are a little bit smaller, we have 50 meters square. Here, as you can see, we also have a wave mode on the bottom left, and we have quad-pole capabilities at L-band, but that will be only acquired over some small particular areas. This is still to be confirmed. Exactly what will be the scenario, but there could be a margin from some particular campaigns, as it's already the case with Sentinel-1. We have also missions that are not flying anymore, but we are still providing the data and improving the data. You have ERS was launched in 91 until 2000, ERS-2, 95, 2011, and Envisat 2002 and 2012. We even have a couple of trainees, Henri and Yves Louis, here, just started, and you can ask them questions. They know very well about these missions. I'm presenting them because we have 2 decades of data that are available. It's more than 1.3 petabytes on level 0 data, 6 million of bulk processed at level 1. You can get the data and all the information on the ESA website. It's the same type of website where you find information for biomass or the Earth Explorer. You have also the possibility to generate data on the fly because we have all the level 0, but we're improving the processor time to time, so you always get the latest version of the data. You can tune a little bit the parameters and see some data that have been already pre-processed during processing campaign in the Explorer that you can find on the map and for all the Earth Explorer missions. In terms of improvement there, we have recovered some additional data that was hosted by different stations that were not having at ESA to have really the maximum of data locally to cover all the data that was acquired between ERS-1, 2, and Envisat. We have a big activity to re-engineer the SAR processor of these missions. It will be open source, GPU based. We have a first version today. We will open it to the public during 26. If you can see the number on the right, without reading, writing, we can generate an IMP image, computer IMP image in 1 second. So it's a big improvement beyond the fact that it will be open source. We'll continue to improve the quality, align the format with the Sentinel missions. There will be a new file format for all the Sentinel missions that will be ZAR based. And we'll add this file format, define a file format for also this mission to be able to work with all the missions with similar approach. We have a new processor also for new product analysis ready data. Will be normalized radar backscatter. The processor will be open source here again and in Python. We'll start generating this data this year in 26. We are consolidating it. We'll open to the public. And there will be some bulk processing ongoing already even of predefined region for thematic areas to support some project like the CCI project for snow. So we use the on-the-fly generation to generate large campaign. The long term for this SAR mission is the direction of fundamental data record with consistently reprocessed record with uncertainty, quantified sensor observation, calibrate, and located in time and space. What does this mean? There are 3 aspects. First is the aspect of composite, putting ascending, descending data together, allowing to build time series of calibrated data, for example, at C-band between ERS-1, 2, Envisat, Sentinel-1, and in the future, Sentinel-1 NG, and cross-calibration between these different missions are not overlapping in time. It's quite challenging. And the third point, which is the possibility of having cross-mission, putting different mission data together, which is this concept of virtual constellation, which is very mature for Sentinel-2 Landsat, for example, but which is just starting for SAR. We could have ERS, Envisat, and RadarSat 1-2, or Sentinel-1 and RCM, and why not NISAR and Roselle in the future. And for this purpose, there was a new COS ARD product that was recently defined. It's under finalization today, which is multi-source backscatter. The idea is to generate that type of image here. You have like this composite ascending, descending of Sentinel-1 that was made for 3 different dates, and you can follow a little bit the change. You have some topography that have been corrected radiometrically, so it's something ready to use, to be used as an input for any scientific analysis. And also the possibility to add different missions together that would be almost on the shelf to increase the coverage of all the revisit time. Here is an example of Sentinel-1A, B, and RadarSat 2. So as a conclusion, we can see the Sentinel-1A, 1C are performing very, very well. The performances of Sentinel-1C are even better than Sentinel-1A and B. This instrument is 10 years younger. It's more stable. There's a lower noise floor. Sentinel-1D was recently launched. The commission is ongoing, and the data will be provided from April, and Sentinel-1A will be decommissioned after that. Sentinel-1NG will take over and enhance Sentinel first generation. Harmony, which is 2 companion satellites, Sentinel-1 will be launched in 2029. Roselle then will come in 2030, hopefully. And ERS and Envisat are still improved with new processor, new products, and it's getting well. Thank you for your attention.
Okay, great. Thanks a lot for giving this overview. As you said, it's challenging with so many missions ESA has. However, we are still able now, because you kept time, very good, thanks a lot, Clément, kept time, so we have opportunity for some questions. Not many, but at least urgent ones, if you have. If you don't have, I could start just to have one question, because we are here a porometry community, actually, and you already mentioned that we have Sentinel-1 NG, which have porometric capability. Is there already some plans how the acquisition strategy would work, and how long, how much C-band fully porometric data will be available for the community?
No, for Roselle, we plan to have some acquisition over forested areas, for example, or they could be over snow, some area where L-band have really use. For C-band, it's not, for me, it's not very clear today. But if there's some recommendation, if there's some interesting use case coming from the community, that will be taken into consideration.
Yeah, I can just very spontaneously think about agriculture applications. Could be very, very useful, actually.
The volume of data might be much bigger. There might be, like always, some degradation of resolution, for example, using quad pole compared to dual pole. So it cannot be everywhere. We have the same issue with Roselle, or NISAR is in the same situation. But for some use cases, yes, it will be possible, it will be supported, and every idea now or later will be considered.
Yeah, I think this could be also something for the talk of Orca later on, where we can also define regions of interest, which could be very helpful, actually. Mm-hmm. Thank you. Are there, meanwhile, a question? If not, then...
In fact, just to add, if there is a floor where we expect, we hope to get recommendations about the strategy of acquisition for polarimetric acquisitions of a Sentinel-1 next generation or Roselle, it is really here. So don't be shy and there talk.
Okay, good. So then, thanks again, Clément. I think we can now close this. And we are now asking the next speaker to come on the floor, which is Marco Laval, and he will provide us an overview about the NISAR mission.
Thank you, Irene. Good morning, everyone. So it's a pleasure to be here.
questions. So the next talk is by Ake Rosenquist, well-known scientist and working at JAXA, and will be talking about the ALOS 4 Pulsar 3 instrument.
Yeah, thank you very much. So my name is Åke Rosenqvist, and I'm representing JAXA, the Japanese space agency. I'm based in Tokyo. I work as a contractor to JAXA and others. I have a little company called Solo Earth Observation, because I do it solo. Okay, so I'll give an update on the ALOS 4 Pulsar 3 status, and with a little bit of emphasis on the operational capacity of polarimetric radar. So first of all, I mean, JAXA and Japan have had a very long tradition of L-band missions. I mean, it started back in 1992, so kind of more than 35 years ago almost, with the launch of JORIS-1 satellite, which was a single polarization L-band SAR, HH polarization. It had two operation modes, on and off, which made it very easy to do the planning. And it actually produced a lot of very interesting pathfinder data that has kind of helped us to get to the point where we are today with this kind of extensive knowledge of L-band SAR. After JORIS-1, which operated until 1998, we had a gap, and then we had the ALOS 1, Pulsar 1, operating. And then following that, the ALOS 2, Pulsar 2, which was launched in 2014, and it's still in operations. And then in 2024, 1st of July, JAXA launched the ALOS 4 Pulsar 3 mission. So there is a rich archive of L-band data, and a lot of that is actually publicly open. And unfortunately, the ALOS 2 and the ALOS 4 data are still commercial. But if you're part of the research program, that is available. And also JAXA ERC are producing a lot of products that are publicly available, such as global mosaic products. Mainly the mission objectives of JAXA's missions are, the main mission driver is basically crustal deformation. You have a lot of earthquakes in Japan, a lot of volcanoes. So that is kind of one of the main mission drivers, is to look at crustal deformation and disaster management. But also we have a very strong emphasis on the global environment, so forestry, wetland, glaciers, and agriculture monitoring. And also to some extent maritime surveillance, mostly in the waters around Japan. So this is what ALOS 4 looks like. So as I said, it was launched 1st of July in 2024, has a design lifetime of 7 years. But of course, we hope that it will operate longer than that. It's in a sun-synchronous orbit with a 14-day repeat cycle. It's placed in exactly the same orbital plane as ALOS 2. So right now, with a 14-day repeat, the delay offset compared to ALOS 2 is 6 and 8 days. So it's actually not 7 days. It's every second orbit is 6 days, and every second is 8 days. The orbit is kept within an orbital tube of plus minus 500 meters. And so far, with the exception of during some debris maneuvers, the 100% of the orbits have stayed within the 500 meter orbital tube. ALOS 4 has kind of possibility for both left and right looking, personally, I'm not very much a fan of that. I mean, I prefer to go for one mode and always acquire data in the same with the same geometry. However, mainly over Japan, there are say, base mapping done in both left and right looking, both in order to mitigate the topographic kind of issues, or like layover and shadowing from both directions. So JAXA are collecting kind of pre-disaster maps on an annual basis in both right and left looking. There is a great compatibility between ALOS-2 and ALOS-4, and you can do interferometry between the different modes. The only mode that doesn't work is the ScanSAR mode. So you cannot do ScanSAR ALOS-2 and ScanSAR ALOS-4 interferometry, but all the other combinations work. So these are kind of the operational modes of ALOS-2, of ALOS-4. And I've put in red circles there. Those are the quad pole modes. So basically, you have possibility to do quad pole at 3, 6, and 10 meter spatial resolution. The main mode currently used for the polarimetric mode is the 6 meter 42 megahertz mode. In terms of calibration, we have a very stable, the geometric accuracy performance is very similar to that of ALOS-2. And we're having basically a 1 meter standard deviation over time in the slant range and the azimuth range geolocation error. In terms of radiometry, it's also very stable. So basically, it's within 1 dB. I forgot to put it here on the slide, but the noise equivalent sigma naught for the HH is about minus 38 dB, and for the HV is minus 37 dB for the 10 meter mode. Polarimetric performance. So we have a good HH-VV amplitude ratio of approximately 1.98. The phase difference is about 1 degree. And the crosstalk is very low. It's about minus 36 dB for the different beams. So I'd like to mention something that Marco mentioned for NISAR as well. We are also using dithering, or we call it variable PRF, or initially. But however, it resulted in some azimuth ambiguities that, at least so far, JAXA have been unable to fix. So we have gone then to a fixed PRF instead for all the observation modes. But as Marco mentioned, we have then kind of these no-receive blinds that occurs during pulse transmission of the next pulse. The width of one of those blinds is about 10 kilometers. But on the other hand, you can see that there are, maybe, I don't know how well you can see it, but the radiometric performance of the fixed PRF mode is very similar to that of the ALOS-2, where you have very little azimuth ambiguity. If we look at the PRF operations then, so basically the solution then, I mean, because of course we don't want to have these black lines kind of in the data when we acquire. So basically the solution has been to augment the acquisition plan for ALOS to use different PRF during consecutive cycles. So basically you have one area or one path acquired with the PRF1, like here in this case, this is the quad pole mode over Stockholm area. And this is the PRF2 mode. So no receive blinds, they don't occur randomly. I mean, you know where they will occur. It depends on the PRF that you choose. So basically, by augmenting the observation plan, you can actually then mitigate the problem with the no data. So, and in a way, that's actually quite nice, I must say, because it means that you, at least for us, I mean, we are not acquiring data every cycle. We don't have that capacity like NISR has. But it means that we are acquiring data instead 2 consecutive cycles in PRF1 and PRF2. So you have, for instance, in the quad polarization mode, you have operations basically in the quad pole mode, you have a swath width of 100 kilometer. In the dual pole mode, it's 200 kilometers. But so we use 2 different beams. We call them HQP 6 and 8, operating at then different incidence angles. We always, for the rest of the globe, with the exception of Japan, we are going for right-looking descending for the quad pole observations. And we're then alternating between the PRF1 and PRF2. And the nice thing is that you can actually then do interferometry, quad pole and Polinsar interferometry in the no-gap areas over these areas. So basically, the basic observation scenario that JAXA has implemented, it is focused then to cover JAXA's strategic objectives for the mission. So cross-site formations, disaster assessment, global environment, and marine applications. And it comprises a variety of different modes. But for the global fully polarimetric data, we have this global base map. So basically, it's one full global coverage of quad pole data per year in each PRF1 and PRF2. So there is a nice opportunity to try out Polinsar at L-band over any site of the globe. We're also having a research program. So we have, JAXA have a research program called the Earth Observation Research Announcements. And within there, we have a program that we call the Kyoto Carbon Initiative. It's actually one of the oldest SAR applications programs that we have undertaken. It actually started back in 1995. So we've been running this program for more than 30 years. Initially, we started it. It was called the Global Rainforest Mapping Project because we had some crazy idea that we could acquire data over the entire tropics. You know, back 30 years ago, that was a crazy idea. Today, of course, it's all missions do that. But you know, back in 1995, all the missions, they were only acquiring data where scientists were asking for data acquisitions. So it was very fragmented. You couldn't do, I mean, unless you were a PI of those programs, it's very hard to find any kind of useful data in those very old archives. But JAXA then, or NASA it was called at that time, actually became a pathfinder and started to do these global observations and systematic observations. Actually, even before Landsat did it. So I think that's something to be recognized. Within this Kyoto Carbon Initiative program, we're actually having a quad pole activity. Where we have collected, so the scientists have suggested a number of sites that you can see there, over which we are collecting a time series of quad pole data then in both PRF1 and PRF2. So you have typically monthly data over these areas. So there is also a great opportunity then for INSAR and Polinsar over these sites as well. So just finally, I mean, as I mentioned, data access to Pulsar 2 and Pulsar 4 data is not publicly open, unfortunately. However, JAXA is conducting research programs, and we have a new announcement coming up in the March-April timeframe. So if you're interested in accessing and trying out ALOS data, please do submit the proposal to this program. Keep an eye on the JAXA website for the announcement. So basically, it will be open in March, April, closed, I believe, in May, and research and data provision will start after evaluation around October. I think that was it. So in summary, so the Pulsar 3 swath, it's in polarimetric mode, it's 100 kilometer, and that's a major improvement from the Pulsar 2 and the Pulsar 1. And it provides regional coverage in 2 cycles, in 28 days, and meaning 4 cycles then with the fixed PRF gap filling. The ALOS 4 basic observation scenario provides 2 global quad pole coverages per year in the 2 PRF used. We have historical data. Then, I mean, we have a near global coverage collected with ALOS 2 Pulsar as well. It's mostly single date data, but it's there. And as I said, data access through the research program. I think that was it. Nailesa Vala, thank you very much.
Yeah, thanks a lot, Orge, for this great overview of what ALOS can do, specifically the different ALOS types. Thanks a lot. Are there some questions from the audience? Not really. Yeah. Yeah, we have.
I have been for 35 years running the SAR missions, and I wanted to publicly thank for what you said. As JAXA and ALOS was a pathfinder to have those systematic acquisition. It took time at ESA for us to implement that with ERS Dynamisat. We have finally implemented that with Sentinel. And we will carry on, I believe. Yeah. But that was not easy at that time to convince indeed that systematic acquisition, regular acquisition was far better for everyone than each user asking for its data. So I just wanted to mention that. And also, by saying that, I want to also highlight the fact that it's important to influence the mission manager, not when the mission is flying, but before. So because usually the acquisition plan are decided well before. I suspect it's too late for biomass. I look at Klaus. I'm not sure you have margin for changing, but you can try. At least at ESA, I believe that still the time is there for Roselle, probably. And even that, I'm not so sure. But those conferences are the right forum to influence the future acquisition plan. When the mission flying is often too late. So don't miss the opportunity for the future mission. Again, thanks for that, I would say, pathfinder role.
Yeah, thank you very much for that acknowledgement. I mean, it was indeed a big struggle to actually, even at JAXA back. I mean, it started with the JRS-1 satellite. It was actually quite nice. I mean, that was the first L-band SAR, or the first SAR of JAXA. It only had a design lifetime of 2 years. So after 2 years, the mission was over, but the satellite was operating. So we were actually called into the directorate, and they said, hey, look, we have this program, and we have the satellite, and it's still working. What do we do with it? And then we came up with this idea of acquiring data kind of over large areas. And that gave us the idea that for ALOS 1, then we wanted to implement that. But initially, we had a lot of pushback for that. And I remember the first PI meeting that we had when we presented that. There was a lot of voices against that. But then the second PI meeting, everybody were happy. and it really made life much easier, and it really accommodates for users. Basically, I mean, now you can find a consistent time series of data for any point of the Earth. You don't need to have been kind of part of the program from the beginning. Anybody here can find any site on the globe, and you will find a consistent time series of Sentinel-1, NISAR, ALOS data there, and that's because of systematic observations. So yeah, that was great. Thank you very much.
Yeah. Okay, yeah, thanks a lot.
So thanks, Take. I will now call the next speaker, Olivier Don. Olivier is a former PhD student of Eric, I think, and now he's contributing to the re-implementation of the polarimetric routines of Polinsar Pro, at least the selected ones, for Python, following a recommendation from this community. And some of these have been already implemented on MAP, and hopefully can be tested next week during the course. So thanks, Olivier.
Okay, thank you for the introduction. My name is Olivier Dont. I work as a freelancer mainly on software and data science for SAR and remote sensing. And today I would like to introduce a collaborative effort to modernize Polinsar Pro by porting it to Python for research and education. So before talking about the new version, let's say a few words about the original version. So Polinsar Pro, many of you already know this software. It's a reference software for polarimetric processing. It has many state-of-the-art, most of the state-of-the-art polarimetric processing methods, decomposition, filtering, and so on implemented. And the main author is Eric Potier, who has started this work in 2003, so a very long time ago. And he allowed me to steal a little bit from his presentation to make this intro slide. And I thought it was interesting to show you a few technical characteristics of the software. Actually, it's written in C, and it's quite a big software. You have like more than 800 routines in C and so many lines of code. And also works with a graphical user interface written in TCL TK. But after 22 years of development, Eric no longer wants to continue the adventure. So that means that as of 2025, the software is not developed and not maintained anymore. And Eric did not want to be a part of the new projects either. So we might wonder what happens next. And next, we have the Python version of Polinsar Pro. So it has been decided in 2021 at Polinsar to re-implement selected functions in Python. And we have a few requirements for this version. It has to be free and open source, publicly available to the community, of course. So we have a nice GitHub repository, we have a documentation website, and so on. The license needs to be non-polluting, so that means it needs to be very permissive. Of course, the outputs need to be similar to, maybe not identical, but at least similar to the outputs of the C version. It needs to have reasonable performance because we change in language. Python is an interpreted language, so we have to take care of having a reasonably good performance in comparison with C compiled code. And also it has to be MAP compliant, so that means that users should be able to install it on the MAP platform and process their data on the cloud. And finally, it needs to work with biomass data. So a small comparison between the two versions. So the C versions, as I was saying before, is mainly relying on the graphical user interface in TCL TK, whereas the Python version is more like a command-based toolbox instead of a software. So although it's command-based, we try to make it as user-friendly as possible. In terms of the performance, The C version has parallel execution explicitly written in the code with OpenMP, and it also has a block processing mechanism, which is also explicitly written in the code. So that makes the code more complicated to understand. Fortunately, in Python, there are a few packages that we may rely on, and especially Dask, which allows for parallel block processing almost out of the box. So that means that we don't have to overcomplicate the code to have good performance. The metadata is carried in the original version in text configuration files. In the Python version, we tie this metadata to the data, to the raster data, using X-array datasets. And finally, the C version has a simple binary format, and multiple files are inside a folder that represents the outputs of a decomposition or covariance matrix and so on. Whereas in the Python version, we have everything in a single netcdf file. Finally, because we are using Dask, we have this feature, the nice feature of lazy executions, which enables scalability to large datasets. So a small software consideration here. Just want to explain why we are using what we are using, what we are not using NumPy. So NumPy is very famous, is very commonly used in the scientific community. It allows you to avoid writing for loops, which would be terribly slow in Python by vectorized operations. But it has also some shortcomings. For instance, you cannot really attach metadata to your data, so you don't have the polarimetric type like a scattering matrix or covariance matrix encoded along with your data. So it's not completely safe for the user because the user might make mistakes and the software would not output any error. The traditional way of storing covariance matrices, so images of covariance matrices or coherency matrices in NumPy is to store those 2D images of 2D matrices, which takes a lot of space and memory. And because we are dealing with Hermitian matrices, there are some properties that allow us to store less information, but we need a proper data structure to do that. And finally, big shortcoming is that we don't have native parallel processing in NumPy, so it does not take advantage of all the cores of your machine. So now Dask array. Dask array is the next step. It has a NumPy-like syntax, and it allows for parallel block processing, which are called chunks in the Dask terminology. So you can see here on this figure that a Dask array is basically a set of chunks, which are NumPy arrays. And once you have the data in this form, well, Dask will automatically block process it and in parallel. So that's almost working out of the box, and it's scalable and it has lazy operations, so nice properties. But still no metadata, coordinates, labels that should be attached to any remote sensing data. So in the end, we are using X-array dataset, which is a layer. We can see it as a layer on top of Dask because it's compatible with Dask. Actually, an X-array dataset is a set of multidimensional arrays, which are characterized by their names. So instead of indices, you can call them by names, access them by names, which is more intuitive. And they have coordinates attached to it, so you can put latitude, longitude if you need. And there are also attributes which are representing the metadata of your image. On top of that, X-array is based on the netcdf data model, so it sounds quite natural to use the netcdf format for Polinsar Pro. And this is an example of a dataset inside Polinsar Pro. So this is an example of a 3x3 coherency matrix. So you can see that there are coordinates attached to it. So here it's an example of geocoded coherency matrix, and you have latitude and longitude along with your data. And you also have the data variables, which corresponds to the different elements of your matrix. And as you can see, we don't have to, because it's a Hermitian matrix, we only need the diagonal elements as stored as real values, and the upper diagonal elements stored as complex. So compared to the NumPy approach, we save a lot of space. And you can also see that this data contains actually task arrays. Pointer here, task arrays which are ready to be processed in parallel because they are already in chunks. And finally, we have the attributes, so we can encode the polarimetric type, which we call pol type as in the original version. So that makes the access to these elements quite intuitive because we can use a dot notation, for instance, for the T matrix, because you can use M12 instead of this NumPy traditional indexing. And for the scattering matrix, the S matrix, you can use, for instance, .vh instead of working with indices. So that's much more intuitive if you want to develop your own functions. And we also have the same notations for the polarimetric type and the descriptions. So this is an example of basic usage using the Cloud Potier HI alpha decomposition. So basically you see that it's quite simple to apply to your data. So we assume that we have a netCDF, so we distribute an ALOS1 sample data set, which is directly a netCDF that can be opened with the software. Then we apply the H-alpha operator that detects that it's a net matrix and internally converts it to the coherency matrix, which is the normal input of the decomposition. And then you can access your, the parameters of your results by typing their name with this dot notation. So for instance, here the entropy that you can plot either with the X-array plotting functions or matplotlib. If you want to import your own data, which is not netCDF, we have a simple workflow to do it. So instead of writing many readers, we take advantage of the fact that Snap is reading a lot of third-party emissions. So you have to open your data in Snap, apply radiometric calibration, export to netCDF beam, which is specific to Snap, and then you can open it with this function in Polinsar Pro. And this is a little bit more advanced pipeline. So if you want to chain several operations, you can do that. You convert your S matrix to coherency, then you can apply, for instance, multi-look, refinedly, and then your decomposition, and you can save it simply with this line to a netCDF file that contains all your metadata, coordinates, and so on. So the advantages is the transparency first, because you can, contrary to a graphical user interface, or a more monolithic software, here you are able to inspect your intermediate variables, much easier to debug. Reproducible because you can use script-based workflow that you can share with other people. And extensible, you can obviously, using this data model to define your own algorithms and include them in the pipeline. And finally, scalable because we have this lazy execution on Dask. This is another example to show that we can integrate it with other Python packages. So for instance, here we have a geocoded coherency matrix that has been terrain corrected in Snap and exported to netCDF. And then we can open it in Polinsar Pro, apply, for instance, the PolyRGB, and then with the RAO X-array package, which is an interface between GDAL and X-array, you can save it to a GOT file that you can open in your GIS software, like QGIS, for example. So far, these are the algorithms that we have. We have the Cloud Potier decomposition, we have Freeman-Durden, Vansil 92, the TSVM, Yamaguchi 3 and 4 components, the Cameron decomposition, and the PolyRGB visualization. And we also have 2 filters, the refinedly filter and the polarimetric whitening filter. So for the evaluation, as I said, we try to keep the Python outputs close to the C ones. Of course, we cannot expect to have exactly the same outputs. There are some machine noise because the mathematical functions are not implemented necessarily, don't have necessarily the same implementation in C and in Python. But my colleague Armando Marino is actually making sure that we don't have a large discrepancy between the two data by computing several metrics. So you have some examples here of metrics he's using and numbers on the outputs of the H-alpha decomposition. He's doing also distribution comparison and visual inspection to make sure that we are consistent with the C version. In terms of performance, so I measured the runtime on my on a virtual private server of 8 cores running on Linux, and we have those runtimes compared between the C and the Python version. So we can see that we have times which are quite comparable, and sometimes Python is even quite faster than the C version. So that's a good thing to note. So finally, to integrate, and so here we made a tutorial that combines actually the map integration and the biomass capabilities. So there is a tutorial, a new tutorial in the docs that you can find that does the cloud processing inside the map coding environment, which is a Jupyter Lab environment. This is made possible by installing Polinsar Pro using the Conda package that we also provide, which is on Conda Forge. And on this tutorial, you can learn how to use the Stack API of map to read biomass data on the fly without having to download it explicitly. So basically, you're pointing to the URLs, and you can stream your data without having to download it fully before processing. And yeah, as I said, there is a tutorial that you can see in the docs. So in terms of planned algorithms, we have a number of classification methods, the Wishart classification methods. We also have surface parameter estimation, Dubois and O, and we'll have some other algorithms like polarization synthesis, parametric signature, and orientation compensation, as well as a few more decomposition. But we are open to suggestions. We would like to hear about your feedback about the software and what are your use cases, what features you would see implemented. So tomorrow I will be at the map booth to collect your request and answer your questions. And yeah, basically that here you have all the information. So you have the source code on GitHub, the Conda Forge package, the tutorials, notebooks on Read the Docs, which is a website. You can access the ALOS 1 San Francisco sample data. And yeah, I will be happy to take your questions. Thank you.
So thanks, Olivier. Maybe, okay, I see there is one question there. Quick one, because anyway, Olivier will be here at this information desk about the software from tomorrow, I think, right?
Yeah, tomorrow.
Yeah, so, and in the poster, so you can ask questions also there. But one quick question, please.
Yes, should be quick. Thanks for your work and for your presentation. My question is on an optimal chunk size. Do you have a recommendation, or is there a sort of optimal chunk size to manage that trade-off between loading the data, not loading too much data, and accessing it in a sort of not redundant way?
I didn't really think about that, honestly. There are you can find articles on the net for the chunk size, but for now, what I'm doing is that I'm leaving it to automatic. But you can, of course, try and experiment with it. But I don't really have a recommendation for that. But that's an interesting question, so I will look into it. Yeah, thank you.
Thanks a lot.
Okay, thank you. So just one comment from my side. You have heard that we have concluded the contract with Eric Potier for the C implementation of Polinsar Pro. So something that we should understand also from you during this week is whether we need to maintain both. It would be an effort, also because, of course, now the Python version will grow because mainly we are implementing that, and I expect there will be new developments. So if we have to keep both versions and to keep them aligned, it will not be easy. So we really have to understand from you if it is necessary to maintain also the C version. But we have the whole week to discuss that.
Okay, great. Yeah, thanks a lot again, Olivier. So then we proceed again to the last talk of this session, which is again from Orke. And as mentioned already during this introductory He will talk about a common effort that has been developed within the framework of CEOs to have common test sites where we have all available polarimetric data together, and he will talk about this effort. Thanks.
Yeah, great, thank you. I'll try to be short. I know that we are heavily out of time. So I'll put my CEOS hat on now. So I represent CEOS LSI-VC, which is the Land Surface Imaging Virtual Constellation is called. And CEOS, that's the Committee on Earth Observation Satellites. CEOS is an umbrella organization for space agencies to help with coordination and standardization, etc. So I'm doing this talk on behalf of Magdalena and Francesco as well. And basically, well, I think that this slide is probably not really required for this audience. Just, it was a slide that we put together just to convince non-experts on the value of polarimetric data, and that it's more than just backscatter. I'll skip this one for you. But basically, the bottom line is that despite the great potential of polarimetric SAR, this research field is very much underdeveloped. And it's because there is a scarcity of consistent data sets. There's a scarcity of consistent time series of polarimetric data to undertake R&D. There is a lack of near coincident multi-sensor, multi-frequency data sets to look at SAR interoperability. There is also, at least for ordinary users, there is a complexity of polarimetric processing. There is a high entry level to new users that I think that we as a community have a responsibility to try to make it much more, say, available. I remember when I started, I don't have SAR, I'm not an electrical engineer. So when I started more than 30 years ago with remote sensing, I was using optical data. And when I came into the SAR field, I was reading SAR articles, SAR papers, and it felt very intimidating. There was all these equations, and you thought that, wow, this is nothing for me. This is too complicated. And I think that a lot of people might feel, I mean, today, I mean, as you know, you don't need to be a SAR expert in order to use SAR data to look at backscatter, etc. I mean, the space agencies are processing the data to a level where you can just ingest the data into your GIS or whatever to analyze it. And I think that's where we need to get with polarimetric SAR as well. There is also another point that there is a significant operational cost for space agencies to go for polarimetric data rather than single or dual pol data. I mean, first you have an increased data rate, and also it means basically that when you go from dual pol to quad pol, your swath width goes down to typically half. And that, of course, if you only have half the swath, it affects your operations when you want to achieve high temporal resolution over regional coverage. So we need to be able to convince space agencies that it's actually worthwhile going for full polarimetry. Because the fact is that there is a great capacity actually out there. There's a large number of current and imminent CEOS missions that actually have polarimetric capacity. Most of them for R&D, they are not really using it. But missions with polarimetric capacity, they span all the frequencies, P, L, C, L, and X band, PLSC X bands, I should say. And also recent technology developments, kind of where we have wide observation swaths and at fine resolution and higher speed downlink, actually is kind of, there's a greater capacity today than it was previously to actually go for more operational quad pol observations. So there is a cautious readiness to exploit the full potential of SAR and quad pulsar. And also, I mean, this community, which you are representing, I mean, the ESA Polinsar workshops have been going on for, well, 22 years now, 23 years, I think it is now, right? Since 2003. Also JAXA, with the Kyoto Carbon Initiative, there is an international research program dedicated to pulsar science. Also CONAI, the Canadian Space Agency, ISRO, have national programs on polarimetry. And also we have the users that represent a whole range of different possible applications. So I go back a little bit to what Magdalena was showing earlier, these recommendations from the Polinsar workshop. Actually, I think that they're not only from Pulsar 2023. I think that they are accumulated over the 20 years of the Polinsar workshops. Just kind of, basically, this is what you have asked for. How many of you were at the 2023 workshop? Can you raise your hands? Maybe half the crew, or yeah, okay, thank you. Because at that workshop, then, I mean, you put together a number of recommendations that were put forward to CEOs. So basically, the creation of supersize for polarimetry and interferometry, acquisition of data from different missions with different frequencies, and multi-temporal data, and the availability of free and open data for the science community, and to provide a single access of data, and if possible, provide data or in situ data as well. So basically, in 2024, CEOs received a call from Magda and Francesco asking CEOs to consider these recommendations. And we then decided to try to set up a Pulsar activity within CEOs under the framework of this Land Surface Imaging Virtual Constellation, LSIVC, which I am co-chairing. And to establish a network of Pulsar reference sites, ranging a whole range of different biomes and application areas. If possible, they should constitute sites where we already had ongoing research by CEOs agencies and the research programs. If possible, access to in situ LiDAR data or airborne data were available. And also seek synergy with ongoing validation networks like GeoTrees that Klaus is maybe, I don't know if you will talk about it. You will be. Yeah. Anyway, and then, I mean, we had a recommendation then to the CEO's principals, so basically the managers of the space agencies at what we call the CEO's SIT meetings, Strategic Implementation Team meetings, to then set up a program where we have dedicated polarimetric observations over these reference sites, coordinated under the LSIVC, and to build time series of quad-pol data for Pulsar and Polinsar, using a multitude of different missions, and importantly, on a best effort basis from the agencies. And the long-term vision, of course, is to go from these kind of research sites to more systematic observations of in quad-pol mole over regional or global scales. And then to integrate kind of polarimetry in the actual background, the strategic background missions of the mission observation plans of the space agencies. And also we have been asked to look at the possibility to have simplified data access for this. a single data repository for the quad pole data. I'll talk about that in a later slide. Initially, it will be open to the science team that we have identified. But of course, we would like to explore, at least when it comes to the data that are acquired with publicly open satellites, there should be no reason why the data should not be publicly open to everybody. When it comes to the missions that are commercial, it's going to be a little bit more tricky, but that's something that we will have to work with individually with these agencies, how we can release the data. Also, looking at the possibility of user-friendly product standards, as has already been mentioned, and then as Marco was mentioning in his presentation for NISAR, there is this analysis-ready data. You have this geocoded SLC, etc., this polarimetric radar analysis-ready data, covariance matrix, etc., that could be used and provided for easy analysis. And also, we want to also stimulate the use of further development of open software tools, like the previous presentation, great presentation on the Polinsar Pro, the Python version of that, and Snap, etc. So the current status is that we have established a science team. So Magdalena also showed this slide. We have, I believe, 26 sites across the world, across different biomes for different applications, where we are proposing to collect data that has been done. We have compiled observation requests from the science team for each contributing SAR mission. We have started to coordinate the observation tasking with the Space Agency point of contacts. For P-band, obviously, we have the standard observation plan. We don't need any particular coordination. We have quad pole data being acquired kind of globally, mostly on a routine basis. For L-band, we have ALOS-4 acquisitions already started over the sites, either started now in January or will be starting in April. We have SAOCOM from CONAI, the global observations that has been confirmed. We are still working with ASI, who are responsible for SAOCOM in Europe. NISAR, we don't need any particular planning. We have the observation strategy in place. Mostly dual pole data, however, but there are some areas that are covered in quad pole. S-band, Novasar, we have confirmation. NISAR, the S-band NISAR from India, we have received some positive indications from ISRO. So we are working with them on that. We have on C-band, we have the RadarSat Constellation mission, where we have compact pole data that they will be acquiring over selected sites. And EOS-2, that is the other name for RISAT-1A, which is the Indian C-band satellite that also has quad pole capacity, where we also hope that we will get positive feedback. I'm looking at IRENA here, TerraSAR-X and TANEM-X, hoping for this, yeah. So I think we talked about this at the LPS last year, but we haven't since. So I think this will be a green tick at the end of this week. Good. No pressure. Okay. And Cosmos Skymed, again, we'll be working with ASI to try to get some quad pole C-band expand data. I mean, as also was said, as I think Clement you mentioned, of course, when it comes to quad pole data, the longer the wavelength, the more use for the quad pole data. However, there has been very little research undertaken on the potential for certain applications of C-band or X-band quad pole data. So I think it would be of great interest to assess that. So I hope that we will be able to do that. And we are also working with CEOS, what we call the CEOS Analytics Lab, which is a cloud analysis platform. It's funded by NASA as a contribution to CEOS, and it's free for CEOS projects and researchers who are involved in CEOS. And there we are implementing a number of toolboxes on we call it the CAL. So we are implementing a number of toolboxes. So SNAP is already there, IC3, as Michael mentioned, is already there. The SAR calibration toolbox from ESA is there, etc. We are looking at the Polinsar Pro, the Pi Polinsar Pro. So we hope that we will be able to get that into the CAL as well. And more applications and toolboxes can be implemented on request from the community. So your feedback here would be very much welcome. Then just the final kind of point I want to raise is that, we are asking something from the space agencies. I mean, the space agencies are contributing on a voluntary and on a best effort basis. I mean, this is nothing that they have to do, but they are willing to give a try. So we as a community then, I mean, the science team, we have a responsibility to actually analyze all the data that is acquired over kind of the respective reference sites to demonstrate any additional value of polarimetric data versus, I mean, what we want to know is how much better is polarimetric data compared to dual pol data? Is it worth the extra effort? I mean, that's the big question. And the science teams are asked to participate at virtual quarterly progress meetings and prepare interim reporting that we can provide to the space agencies to show that there is progress. If we are successful, we will be able to argue for an extension of this program in 2027. At the moment, what we are asking for is a blanket, basically monthly observations in quad pole mode during 2026. So it's kind of us as a community then to show that with this kind of data, we can actually do something magic, right? So the ultimate goal is to prove to the space agencies that this extra operational cost for SAR, for quad pole SAR, is worthwhile, leading to operational quad pole capabilities for future missions. So this is really a unique opportunity provided by the space agencies, and I feel that it's like a now or never opportunity for this community to prove that Polinsar is something that is really important and that can bring something to the space agencies for the future, for implementation for future missions. I think that was the last. Oops. Yeah, thank you.
Thanks, okay, for this interesting presentation, and also for being quick and efficient. We are a bit late, but don't know if we should allow one question. Or...
Yes, I think we should.
Yeah.
If there's some urgent question, and if not, I see everybody's hungry or getting hungry. Me too. Okay, then we just close it probably.
Yeah.
Yeah.
Oh, there's one. Sorry.
Yeah.
There's an announcement then still.
Yeah.
One quick announcement. We noticed that we messed up the poster list. So if you want to put up your poster, please wait until after the lunch. We will print out a new list during the lunch break. For the lunch, I think we can use the canteen downstairs, the university canteen. You can grab a lunch there. There's also restaurants outside. You can also grab a restaurant, of course. You can go to a restaurant outside, but please be back in time for the next speakers. Huh?
Yeah.
Yes, and if someone of you already put a poster, maybe check the poster list after lunch if you're on the right spot or not to fix it.
Okay, probably at the end we like to thank all speakers for the session and thank you for your participation.
So we meet again here, the same place, maybe 5 minutes later, I would say. It's 2:15.
2:15?
Yes.
Good.
Not much.
Shall we start? Yes.
Okay. Good. Hello. Good afternoon, everybody. My name is Laurent Ferrofamil, and together with Magda Fitzig, the other co-chair, it's our big pleasure to welcome you to this session on Pulsar and Polinsar modeling. And we will have 5 interesting presentations on different aspects of Pulsar modeling and decompositions. And I would like to welcome the first speaker, who is Kostas Karakristos from the University La Sapienza in Rome, and he will talk about modeling scattering of anisotropic soil.
Good afternoon to everybody. Thank you for introducing me. First of all, I'm very pleased to be here and to present part of the work that I'm doing in Sapienza the last year and a half, more or less, entitled Modeling Multistatic and Multipolarization Radar Scattering Over Anisotropic Soil. Specifically, we are focusing on soil moisture estimation, and we are going even deeper to tackle the problem of flushing fields. In fact, today I'm going to introduce you our methodology, that it is based mostly on multistatic diversity by means of information, and of course to polarization diversity. Because this work it is theoretical until now, unfortunately, we have no data to validate it. But in literature, there are lots of methods that validate our approach. I'm going to present you some numerical results, our conclusions, and of course, the work that it is already in progress. So as you already know, soil moisture is very important as a factor, plays a pivotal role in vegetation and agriculture. So we have the need to monitor and to be accurate. Of course, there it is where SAR comes to play an important role. But SAR doesn't measure soil moisture directly. We have acquisition, we have signals, and we need to apply retrieval approaches in order to estimate the soil moisture. So in our case, that we are focusing on bare soils. As you can see, bare soils going under lots of processes during time, and they generate these quasi-periodic patterns. These quasi-periodic patterns is the reason why probably we can observe the problem of the flushing fields. So here, as you can see, we have 2 acquisitions of airborne SAR, the same field depicted in a flight from west to east and with a flight from east to west, but we have a totally different normalized radar cross-section in these 2 cases. In fact, the values are very high in this flight and very low in this one. Flushing fields, according to literature, can born a difference more than 6 dB. So, in order to try to retrieve the value of soil moisture, we have to tackle this problem. And in order to do it, our approach, it is based in a decode of the electromagnetic scattering, a detailed full decode, and of course in the exploring of the information diversity that we can have. In fact, we are trying to propose a model, to apply a model that can realistically represent the bare soil, and we're going to need this model in order to feed an electromagnetic forward scattering model to generate values of normalized radar cross-section that can be, let's say, close to reality. And with these values, with this simulated data, we're going to try to explore most of the information that we can get in a matter of polarimetry and, of course, of the multistatic geometry. So here you can see the representation of a bare soil by applying the double-scale model that it is an isotropic model as introduced by Professor Davide Comit and Pierre Dica. Also in this work, they are helping a lot with Ferdinando Nunziata. This model, in fact, combines 2 components, the isotropic small-scale component that corresponds to the micro-roughness, clods, etc. And of course, the large-scale component that corresponds to the tilted areas, the furrows. As you can see here, if we're going to compare our model with an isotropic case that initially were applied, you can see that we can capture this resonance, these flashing fields, in the case of anisotropy. Maybe a more intuitive figure, it could be this one, in across-track and along-track baselines. So, by means of anisotropy, we have the fundamentals to feed our model. Now, what we're going to use? We're going to use the small slope approximation model, and because we need the polarimetry, we need the cross-pole information, we have to move to the second order in order to generate the cross-pole. So, the cross-pole is very important because, as it is proven, it is different, the dependence on anisotropy. It is very sensitive in the roughness, and this could possibly help us in decoupling the ill-posed problem between roughness and soil moisture. And this could lead us in information diversity comparison to the copole, to the copole components. Here comes also the large baseline configuration of the multistatic radar. Imagine that we have an active master transceiver and 2 passive receivers. So in total, we can have 3 acquisitions. As I said before, because we have simulated data, we need to carry out a sensitivity analysis. From the time that we are not applying a specific algorithm for the retrieval of soil moisture, we are using the tool of Kramer-Rao lower bound that estimates, let's say, the theoretical limit of any unbiased estimator. As you can see, we have here the Jacobian, which captures the sensitivity. And in the Jacobian matrix, every column corresponds to a parameter that we would like to estimate, for example, the soil moisture, and every row to a possible observation that we could have. This is going to be better explained later on in the other slides. And of course, we have also the covariance, but in our case, we are studying the geometry. We want to emphasize in the diversity of information thanks to the geometry. So in order to have, let's say, a system independent, we are not focusing in the noise, right now at least, and with the simulations. So the total workflow could be depicted like this. Imagine that we have our model, that it is, as I told you, the second order. We feed our model, emphasizing in the double-scale anisotropic in order to generate the flashing field phenomenon. And then we have the database. With this database, we're going to carry out the sensitivity analysis, and I'm going to show you the results that we finally get, and they are, at least to me, very promising. So here it is how we started. In the beginning, we were doing some experiments based on a simple case where we are trying to estimate only 2 parameters in a way that we have to tackle a multi-parametric problem with lots of variables. We are assuming now that the only unknowns are the soil moisture and the orientation of the tiles, of the furrows. In such a case, with 2 unknowns, as you can see here, we have 2 columns in the Jacobian, and we are assuming at first stage that our acquisition is only the VV. So we have the active transceiver, that it is here in the axis, in the center, and then we are placing in a fixed position the first passive receiver in a large baseline of 200 kilometers. So we have another acquisition of VV in this position, and then to generate this map, what we are doing, we are placing in every possible position the third sensor, the second passive. So if, for example, we're gonna point here, and we're gonna put here the second passive receiver, in total we have these 3 acquisitions. If we're gonna put it here, the estimation that we're going to have is going to be really, really accurate because it's blue the color. For example, if we're going to put it over here, the estimation cannot be good. But of course, this is a simple example where we have only 2 parameters and we have 3 measurements. In fact, we could expect such a result. Regarding the figures, because they are the results, I would like to tell you that, of course, the blue areas are positioned that shows that the multistatic geometry could work in such a case, while the red ones are the ones that we don't need. So, in fact, this was the preliminary, the initial results. We moved on in the case that it's more important, and it is the case with the 3 parameters, where we don't know the soil moisture, we don't know the orientation of the tiles, and we don't know also the roughness, the small-scale roughness according to the model. So we have 3 parameters, but we have the soil moisture that it is coupled with the roughness, and we have to tackle this problem. Here it is where polarimetry comes up, and where the cross-pole component it is very important, because it's going to offer us the diversity that we need in a matter of information. And in fact, what we did, we followed exactly the same approach by using, a part of the 3 VV acquisition, also the VH acquisition. So we are having, in total, 6 measurements for every possible position that we can put the second passive receiver. And we have 3 parameters that we would like possibly to estimate, but we are focusing now on the soil moisture. Of course, with 6 measurements and 3 parameters unknowns, we could expect results, but not everywhere, and not that really good as it is here. And the reason that they are really good, it is because we can observe positions that we can have good estimation that all of them belongs along trunk, in this along trunk axis. The most important for every result that you can see here, it is that we are depicting the worst case scenario by means of, if I'm going to put here the 3rd sensor, the second passive, I'm going to estimate the soil moisture based on a possible orientation of the field. The thing is that we're going to run an experiment in 180 possible orientations with a step of 1. And out of all of them, we're going to choose the worst orientation of the target that leads us to these results. So this, in a way that is going to make it even more valid. In another word, let's say to explain the same results, here it is a comparison between the multistatic geometry and the monostatic one, where we are using also the cross-pole component. Of course, everywhere the improvement factor, because here we are depicting the ratio between the multistatic geometry and the monostatic one, it is everywhere better. The thing is that it is at least 60 times better. And by running a bootstrap analysis, in the 80% of the situation, this could lead us to very, very good results. So, in total, out of this brief presentation that I could do in this topic, that, to be honest, the origins are many years ago, the outcomes could be that the flashing field could be probably being solved by taking advantage of the geometric diversity, that of course polarimetry could offer an information diversity that could lead us to overcome coupled phenomena and have results that are much better of the monostatic ones. And of course, the thing that it is important, it is that we have an alignment with future missions, for example, with Harmony. Of course, what we need right now, it is to validate these results with a campaign of biostatic acquisitions. And at least to me, what it is a bit even more important and interesting, it is to try to extract even more information from a polarimetric perspective, to generate probably coherency matrices, and also to move, not only to move to vegetated areas, apart from a bare soil, where we have to combine more models. Thank you very much for your attention, and I would be happy to have any questions.
Thank you, Kostas. We have time for questions. Are there some? So it means that I will have some time to ask you questions.
Yes, yes.
So your ambition here is to estimate the parameters combining all these multistatic acquisitions. But maybe a more simple objective would be to at least detect that a field is a flashing field, no?
Exactly. This way.
How can you do this? Did you try to do it?
Yeah, okay. In fact, what happened, there are some results as the one that I showed you earlier. Can I move a bit? Yeah. Perfect. So the flashing field, to me at least, it is a bit weird as a phenomenon because in this picture, just a second, sorry for this. In the very first one that you can see the flashing fields, it doesn't happen that there's a different orientation or, I mean, the flight, if you're going to think about it, it is exactly the same for a different direction. So this cannot tell you, okay, I have a different orientation and this is the reason that I have the anisotropy. But what happens in this flight, it is that the incident angle differ. So according to this, if we're going to, it depends when we're going to have the Bragg resonance according to in the angle case. At least until now, we don't have different orientation to know if the orientation can bring it. But even with this phenomenon, with a different incident angle that we can observe exactly this one, and I ran a process to validate that it's not a change in soil moisture in the specific day that there was a rain or something that brings us in these results, I could briefly, let's say, validate the model, the second order, and I have some preliminary results, but in the aspect of the VV components, if I could may show you, it is in the last ones. And because they are very promising, this make me feel that probably the flashing field can also be generated because of the geometry, first and foremost, even if it's going to be the orientation or even if it's going to be the angle of observation, because it's very relative. And also the bands are different. But I can show you this one. Sorry for this thing. Maybe I can use here. No. So I have also the situation of combining different frequencies, but it's not about polarization in this case. It could be combined as a synergy, Roselle, maybe in L and C band, but it's different, and it could be explained by physics, this one. But I have this very important, at least to me, results that in the very first figure, you can see how the second order small slope approximation by using the anisotropy model could be in line with the results from the SMEX campaign. And the match, it is tremendous, at least to me. By using QGIS and SNAP, I detect the same flashing fields same day without changing in any other parameters, just the intensity, and I could have a very good match that it cannot depict in the case of isotropic, as you can see in the middle one. The most important to me, it is that the HH component cannot have that good fit. And the reason it is because the specific field, that time period, has a bit of vegetation of cones that could generate also the HH in a different feedback. So to me, I'm not talking about everyone in this project because it's huge. I mean, also Prof. Pierdic and committee, they are working a lot with Ferdinando Nunziata. At least to me, it's not the thing of the orientation. It is generally the geometry. In any case, it's exploitation. But from my perspective, polarimetry can offer you information. So the more that you can have, the better is going to be the results in any case. And in a matter of also of geometry.
Okay. Thank you very much. Any other?
Yes. Okay, it works. Yeah. Thank you for the presentation. Just a very quick question. You were using just a standard, let's say, polarimetric basis, the polarization basis. But did you also attempt to use, let's say, a polarization base that's more optimized for large baseline bistatic angles? Referring to the paper from Lorenzo Giannini and also Perdica and
exactly this. Yes. So right now, for example, we use only the VH component because when you're going to generate the values in the bistatic base, the things change a lot. So the most important for me, it is if you're going to go step by step, it is to try to generate in a bistatic base the coherency, the full matrix, maybe the Miller matrix. But the thing it is, if you're going to generate this, polarimetry can offer you the phase. At least from my perspective, this information is the important one. It's not only the intensity that can give you exactly something more, not in the same way that INSAR works, in a different way. Until now, probably there are lots of decomposition techniques that they are trying to extract the information. But if you're going to use the large baselines, you cannot, for example, have your data in a real case study, and you can apply a decomposition in a bistatic format, because it's not a monostatic decomposition of the scattering matrix. It's different. So, or you're going to go with a dual pole, like in Sentinel-1, you can use a dual pole decomposition, and then you have to figure it out how you're going to use the information of a bistatic, or you have somehow to combine all the information in a matter of angles, probably. Because I don't think that it could be possible to use the same approach. For example, any decomposition, the 4-component Yamaguchi, all of them, I don't think that it could be possible to be applied as it is right now in a bistatic case scenario. For example, in harmony, I don't know how it could happen. There are some works, I think, from 2022 and then to try to approach the polarimetric decomposition in a case study of large baselines acquisitions. In fact, to be honest, this is what I would like to do after generating the full Miller matrix, to try to go to decompositions. But this is my ambitious.
Thank you.
Thank you.
Thank you. Thank you very much for your replies.
Thanks a lot.
Okay, so the next presenter is Armando Marino, who will present results from testing different methodologies to decompose pulsar data into a focused partial target plus a residual one.
I think that is the second one. This is the tensor.
Okay. According to the program, this is the other one, but okay. You can present whatever you want.
If I can start with this one. Yeah, no, sorry, I'm confused, but if I can start from this one.
Yes, please.
Thank you. So, that's the pointer.
What do you need?
Yeah. Green. Ah, all right. Oh, no. The pointer. Ah, all right. Very good. All right, thank you. All right. So, hello everybody, I'm Armando Marino from the University of Stirling in Scotland, not far from Edinburgh or Glasgow, if you don't know where it is. Today I'm very happy to present these things. If I can, I will start with this one, which is a little bit more, say a bit different from what you normally see, and then I go to one that is a little bit more conventional. And it's about the tensor field, this heterogeneous target and tensor fields. So motivation for this thing. The main things why we do this is because we have speckle. Everybody knows data have speckles, are these nasty things that don't allow you to do retrieval very easily, but also good for us that we have more to work about so that we can get some work on it. So because of speckle, you cannot, if you don't have a deterministic target, so a target that doesn't really change, it's always the same, you need to use second order statistics. You cannot use the scattering matrix or the scattering vector very nicely, but you need to do the average, and you need to do it properly. And second order statistics with the covariance matrix allow you to do that. So now, what is the problem with this? So why I'm here talking? You do the covariance matrix with second order statistics. So you go to the second order characterization of these targets. This is a quadratic. When you want to calculate the power for each scattering mechanism of interest, so you want surfaces, then you do a quadratic form this way. When you plot all this quadratic form over a basis for your polarimetric data, in this case here, I took the liberty to show this as real, which is not real. So, but imagine you have three axes, and imagine them real because we cannot think complex. So when you want to plot these things, you will have an ellipsoid. An ellipsoid is a quadratic. When you do these things, it has to be a quadratic. It's forced to be an ellipsoid. It cannot be anything else. It cannot have bumps. It cannot have squares or triangles things. It has to be an ellipsoid. What happened here? Imagine you have this type of target inside your averaging cell. So you take this, say, 7 by 7, 9 by 9, 11 by 11, and these are the the scattering vectors inside this cell. So choose 3 colors, don't read anything out of this, it's just colors. So this is the first cluster of vectors bunch up in this direction. The second cluster, say, bunch up here. The third one, bunch up there. And when you do average in all these things, what you get out is that you get this ellipsoid out when you span with your quadratic form, and you will have a major axis, which is not necessarily where your vectors are. You have a second axis, which again, unless these two are orthogonal by nature, what comes out will be orthogonal and don't have to be. And you have a third one here is the minor axis. What you get out is not what you have a start with. So you have distorted this vector so that then your representation thinks they are in this shape here. So the bottom line, what is the problem? The problem is that these vectors, first of all, they don't have to be orthogonal to start with. You don't have necessarily to have surface double bounds and 45-degree dihedral there. They can be different stuff. So this is the first thing. The second thing that we can take advantage of is that they don't need to be completely mixed inside the same pixel. If your 3 targets, even if they're not orthogonal, if they're fully mixed, in each pixel that you have, resolution cell, you have these 3 things there mixed together, then there is nothing you can do. Because if you have a coherent acquisition, you will come out as an ellipsoid, you will have lost it before even do average. They are all mixed. But if they are not mixed to start with, so if you have some patch where you have only come with me, only surface, one where you have only dihedral, one where you have only volume, then you can do more. You don't have necessarily to mix them all together and distort this information. You may want to do something a bit different to retrieve that. And this is what we want to do here. Try to find if there is a way to avoid this indiscriminate average and get out the original information before mixing all together, before averaging all together. So, a few years ago, I proposed this thing. So you want to do a clustering over this vector inside what was your averaging window. So your searching space. And I call them tensor fields because it looks like quite fitting, but it's basically a bunch of vectors, so you want to cluster them. So first things you need to do, you start from the scattering vector, and then you remove what you can call the absolute phase. What you need to remove is the contribution on the phase of the distance. Is what you do when you create the covariance matrix. When you create a covariance matrix, you have diagonal intensity of diagonal, you have the cross correlation, and the phase of those is the phase difference between the channels. Phase difference is good for polarimetry. If you add an R for the distance of range, then it's not good anymore because it changes all the pixels and everything gets lost. You need interferometry for getting back that. So if you remove the phase of any of them, say the first one, or then the first component, then the only difference phase that you have there is the phase difference that you get from the covariance matrix as well. So classic formalism. This formalism here, or used in a covariance matrix with one single look, is B-unique, so you can go from one to another without loss of information. They are the same numbers. Actually, here there's a bit less numbers than there, but it's the same things there. You can go from one to another, so we are not doing anything more than create a covariance matrix with one look. But using vector is better than using those covariance matrices for some reason that I'll also come next presentation. So you have these things, then you want to find where the vector bunch up. So you get for the maximum vector, you see angular distance, you assume you don't want them to be farther than, say, 25 degrees, and then you bunch them up. You remove them, you look at the rest. Go again for the highest one, you see which one is close to that, and you continue. So this can be represented by this equation here, what you do. And it's not very dissimilar to a k-mean algorithm, which I also used for doing this thing. But in this methodology, you are free to choose the theta. In the k-means, the machine chooses the theta for you. So the angle difference. So that's why I prefer this way. But the results are similar of just a k-means clustering. So you see here, this is important. Your covariance matrix that you get out of this is the sum of many covariance matrices based on many targets you want to extract. You say, I want to extract 3 targets, 4. Probably you shouldn't go to further behind 4 because you have a 3-dimensional space. But let's say you want to go for 4. So there will be 3 covariance or coherency matrices. And the characteristic of this is to be very almost rank 1, low entropy type of targets. Why? Because if you see the bunching up here, when you put this together, they are almost very close. So if you have a rank 1, it will be just a single vector. Because this they spread a little bit, then you will have something that is not really rank 1. And, but it is still low entropy. You could interpret these things as target plus noise type of approach. For each one of those, of course, not for them all together. So you put them together with the classic averaging them. So you do the average after you have clustered them. Cluster first, average after. So some example using biomass data. And so it's very cool new system. Let's use that for testing the algorithm. Took this image from the archive, 16 December. This is Mozambique, I have it here. And this is the quick look you get from the folder. This is the image that how I processed it, so radar coordinates, and the average is not right to make it super square, but I like the number of look that comes out of this, so that's why I did 11 by 3. And you see a lot of sea, forest, some river with floodplain, and this red stuff here is the wetlands, double bounces. So, first of all, let's have a look at this Claude Potier. So classic way of looking at it. And we are looking here the alpha for the eigenvectors. CP stands for Claude Potier, no compact pole, so it's just a bad choice of acronym there. But it's, you see, the first one is mostly a surface, but you have some double bounds for the wetland. And the second one is the dihedral over the sea, which everybody knows why they're formed, right? Non-ideality, they shouldn't be there. But this is forced to be 90 degrees with this. No matter what happens, this will be 90 degrees with this. Even if there is something else, this is forced to be like dihedral. That's it. So, yeah, but you see also the forest, you have the characteristic of being quite confused. Entropy, very low over the sea, higher entropy over the forest, and so on. So, let's have a look at the decomposition. Target number 1, the main cluster. You see it's mostly blue over the sea. The sea is very blue because there is only surface scattering there. It must be blue. Also, a note about what I'm showing here. So this is the main component. You remember those C with 1, all those C matrices? This is the first one of them. Actually T, because it's Pauli basis, represented with Pauli basis. So it's the first component represented with Pauli basis, RGB. Okay? So blue over the sea, blue over the floodplain. You have some reds here for the wetlands. Then we go to the second one. If you look with the same scaling of the first one, you see very little, mostly is gone. You won't actually see something over the forest. I don't know if it can be appreciated from the screen, but all the rest, especially this is basically 0. So let's scale this in a better way for the second image. So this image and the one before, they don't have the same scaling, while this and that did. So if you scale better, then you see there is a lot of reds for the wetlands, and there is quite white type of scattering inside the forest. White means that there is a lot going on. One pixel may be green, then red, then blue. When you put them together in this representation, they look white. So a lot going on. And this is the third one. Again, if you use the same scaling, you won't see anything except a bit in the forest. If you use a better scaling, you see even more nodding over the sea and white for the forest, a bit of reds around. So now let's have a look, not trusting too much the Pauli RGB to tell the scattering mechanism, but having a look at the alpha angle for that target. So this is the alpha angle for the tensor bunching for the different levels, so first, second, and third. So the alpha angle of the first one, so you take that C matrix and you calculate the alpha angle of that. The alpha angle of this one you see is mostly blue, which is what you see a lot in biomass, a lot of surface scattering. And there is some red around wetlands. If you look at the third and fourth, over the C is not a number, so this is nothing. And for the forest, you mostly see this type of green type of scattering, confused, and there's a lot going on, not really, a lot of confused, like volume scattering. The entropy, you can calculate an entropy of this decomposition, which is this one. If you look at the entropy of the tensor entropy, it's not very dissimilar to the Clopot-Tier entropy, which is this one. It's a little bit, so look at this, keep in your head, and the next is coming here. This is a little bit darker, if you see. So there is a little bit better separation because you cluster them better than before, getting the ellipsoid and then let the ellipsoid cluster in them. Here you are really taking you're really taking the separation a bit better, a bit more pointed to where they are. You can check if your reconstruction is good. So this one is a data-driven approach. You pull out these targets. They may not have the full power, so you can check that what you get after 3 components, how similar it is to the full power to know how much you characterize of it, and looks like pretty good. In the forest, maybe you lose something. And also another things you can plot is a sort of depolarization tensor where you have the power of all the rest over the power of the first, to have an understanding a little bit where you have just one scattering mechanism when you have more. And these things I need to skim through very, very quickly. But one thing that I wanted to do is to see, can this be used for detecting and maybe cleaning RFI? Because this happens in biomass. So I took a scene in Kenya where you have quite a lot of RFI, and saying this is probably, we need to live with it. This is the nature of the thing. In P-band, you will have them. But you can correct them by removing some spectrum, losing resolution. Can you do this without losing resolution? That was the point. Punchline at the start, no, it doesn't really work well. So you see, well, I need to be very, very fast. But the first component, you have these blue things. Now, if it was all in the first component, job done. Throw them away, you take the other components. The problem is that it's not true. You also have them in the second component. It looks different from the first, of course. It is greener here. And you have them in the third component as well. They are full rank. They are everywhere. They are annoying. More has to be done. So this cannot be used straight away for doing that. But I want to think about this more in the future and see if we can help. And okay, I think this one we can just skim through. And that's it, I'll close here. Thank you for your attention.
I think we are a bit short of time, so maybe there is no, unless there is a quick question from someone. Yes, please, Kostas. No.
Can you? Thank you very much. It was very interesting to me. Generally, I think I would like to ask you something. First of all, you are talking about tensors because you are moving more in 4D, let's say. Yeah. So, have you ever thought about to take an approach that also Cameron used with the Riemann sphere in order to depict it? Because in the beginning you said that this is a simple approach with Pauli. In reality, we cannot, let's say, present this thing with a 4D. So if it could be useful. And the second one that is very quickly. In fact, this, if it's going to be simplified, it is the space of the sphere doing a principal component analysis, that it's the simple case not moving to tensors, if I understood well.
Yes, so first one first. Can be done in 4D. Yes, you just add that dimension. Is it useful in 4D? I don't know. We can talk about it, but the approach is scalable. The second thing, this, because you don't want to do a PCA. Clopot here does a PCA, so you have two vectors, and then it makes them look like this. But they are this. But what PCA, what it does, it creates a coordinate orthogonal. We don't want to go there. We want to separate before we put them there, and then we sum them after that we have separated them. Does this answer?
Yes, in order to not make it deterministic, you don't want to separate them. To say one vector over there that probably corresponds to a deterministic scatterer, that it could be.
Yeah, but here you could say that this one are deterministic scatterers too.
Okay. Yes.
So each one of these blocks that you come out, they are low entropy targets. Now, depending on the way your physical model at the start to it, they could be interpreted as patches of different targets. So I also forgot to stress more that this works when you have patches of targets. If they're fully mixed, then forget about it. You can extract things that are not real. Yes. Okay. So, but you can interpret them as like a patch of surface, deterministic, patch of double bounds of a building, deterministic, and so on. Does this answer?
Yes, thank you very much.
All right.
It has to answer.
Thank you very much. Thank you.
So the third paper of this session will be presented by Vahid Abkari from the United Kingdom and the University of Stirling, and it will deal with quad-pole data reconstruction.
Hello, everyone. Good afternoon. Very welcome to this presentation. I'm from Stirling University again, like Armando. So what I'm going to present is my PhD student work. So the main focus was to reconstruct quad-polarimetric star data from compact pole data using deep learning techniques. So I would like to acknowledge my collaborators, Armando, Sahar, Mina, and Iman. So this was a collaboration between all these people. Oh, yeah, sorry. Okay, so just briefly, I want to say that, so we know that from quad-pole data, we get rich scattering mechanisms, but quite narrow sweat, whereas from compact pole data, we get twice the coverage, but we have less richer polarimetric complexity. And this is what operationally we prefer to have dual pole data because of the coverage, but at the same time we want to have the richness of the compact polarimetric star data. So the main point or goal of this work has been to reconstruct quad pole data from either compact pole data or dual pole data. So, the challenge is that it used to be done by statistical methods. So this is, we want to go from 2x2 scattering metrics of compact pole data to 3x3, quad pole matrix data. So it's just ill-posed and underdetermined system. So we cannot do this directly. We need to have some assumptions like reflection symmetry or some mathematical approximations. So this is the challenge. So it used to be done by people like Soris in 2005 and also Nord in 2009 that they proposed some statistical model or physical-based methods, but these are relying on mostly reflection symmetry properties of geophysical media. So they also assume some linear relationship between cross-polarization channels. So this is the major fail of using these methods because they will fail in complex scattering mechanisms like in urban areas where the assumption that they have will not hold anymore. So what we propose here is that our approach leverages the unit architectures, which is the standard for many image-to-image translation in remote sensing and image processing. So these models are highly effective for SAR despickling or super resolution and some other applications as well. So we treat this challenge as image-to-image translation. So to go from compact pole data to quad pole data. So these are just sort of unit-based variants that we have chosen for doing this reconstruction task. So all these models trained and tested against the ground truth quad pole data. They are relying on, not relying on those assumptions that we had from physical-based methods. So in this work, we have tested all these, unit-based methods on our quad pole data. So this workflow shows what we have done. So we have pre-processed the quad pole data, and then we have simulated compact pole data from this, from the quad pole data. So we have done radiometric correction, calibration, and speckle filtering, and we have generated covariance matrices from this. And then we have done geocoding. We have extracted patches that can feed into deep learning. And then finally, we do validation. But before that, we have trained our deep learning models. Okay, so to assess the success of our work, we have used the standard matrices like mean square error and mean absolute error to measure how good our deep learning method works in terms of reconstruction of quad pole data from compact pole data. We have also used the peak signal to noise ratio to measure the quality of our reconstruction. And also we have used complex correlation coefficient to check the preservation of the phase information between channels. So just to say that because we have done on all those 9 elements of covariance matrix, so we have calculated all these matrices one by one for each element, and then we have taken average of these matrices. And also we have used the Hartley-Lowry trace statistic to understand how how significant is if the similarity between reconstructed covariance matrix and true one are significantly similar between these two matrices. So this is just the Hartley-Lowry trace statistics that is used to indicate, to measure the similarity between these two to reconstruct on truth data. So we have chosen San Francisco because it contains all those major scattering mechanisms like double band scattering in the urban man-made structures, water area we have surface scattering, and we have volume scattering from vegetated areas. So this is a nice test site. So these are our satellite data that we have collected, 2 LS2 and RIDESAT2, to have 2 different wavelengths. So of course the incidence angles of these 2 data sets are different, but what we do is that we have trained and tested LS2 data, and then the model that we have obtained, we have tried to use on RIDESAT2 data. So, so this is the result that we have got using the Soris method. And you can see the ground truth quad pole data and reconstructed one. And looking into HLT similarity map, you can clearly see that there are differences, especially that the HLT values have got very high in where we have got those red pixels, which are located in mainly urban area, but because in those pixels reflection symmetry is the assumption that the Soris hasn't taken out time. Because of this, we have got this result. But looking into deep learning based method that is called the ResUnit, that uses residual blocks, so you can clearly see that these 2 results of ground truth and reconstructed one, they are pretty similar. But of course, in the open water or surface area, you can see that compared to Soris method, the HLT values or similarity metrics that we have got are slightly higher than Soris. It seems that the deep learning methodology doesn't handle well. But outside that area, in urban area and the state areas, we have got very good results. So these are just comparing these 3 methods, physical-based methods and the residual unit. Just I'm showing the residual unit, which we have got the best performance from that. And in the bottom row, we see this HLT or error map of similarity between ground truth and reconstructed to see how we have done this work and what we have got. So you can clearly see that in urban area, man-made structures, the Soris and and slightly north has failed, whereas the RES unit has worked better in urban areas, but in the middle, where we have open water sea surface, it seems that the physical-based method has worked better. So looking into these matrices that I mentioned, mean square error rate, mean error, absolute error rate, complex coefficient, and the signal to noise ratio, you can clearly see that the RES unit is giving us the best result with lower MSE and a high complex coefficient compared to physical-based methods. Again, so the RES unit was not the only one we tested. We also tested other unit variants, but they will not perform well. So the RES unit was the chosen model that that performed better than others. I think because it uses because of the use of the residual connections, it lets network learn better the difference between input and target. And it also helps the capture polarimetric corrections and stabilities better than the series methods and NORD as well. So we also looked into Calotte-Pettier S-alpha planes for all of these reconstructions. So looking into true quad pool data, you can compare it with others, and among all these 5 methods that you can see here, residual unit has got more similarity, especially for the urban area and where we have got double band scattering, whereas the series NORD, because of that reflection symmetry, we have less similarity with true quad pole data S-alpha plane. But again, as I want to highlight that the RES unit was the best in terms of this, but the attention unit hasn't worked. This is still in progress. We want to understand what happens that we don't get the best results in terms of this decomposition. What we did next, we tried to use the model that we trained on ALOS Pulsar data on C-band radar satellite data. Of course, the model has learned the L-band data, not C-band data, but you want to see how general the model is. So you can see the results on these 3 data, radar SAT2, quad pole data, through quad polarimetric data, Pauli image, and then the other 3s. And you can see that especially the unit has worked better than others, but in the surface, the series NORD has failed more. And especially in these red pixels where we have urban area pixels, it doesn't present very well, and it doesn't handle those pixels compared to residual unit work. So looking into HLT map or similarity measure between true and prediction, again, the residual unit consistently outperforms across different bands. The bands means those 9 elements. That this is just we have got these values, the average over 9 elements of covariance matrix. So what we did next, so we just wanted to look closer into 3 urban vegetation and surface water. So this shows one patch of urban area that you can clearly see that looking into SLT map or similarity measure in the second row, the NORD and Sirius, the Sirius has failed because of that reflection symmetry assumption, but the residual unit has worked better. So this is surprisingly, I want to highlight here that this is that we have trained the model that we have got from ALOS Pulsar data, and then we tested on radar SAT2. And this is the over-vegetated area that you can clearly see that again, residual network residual unit has worked better than Sirius and NORD method, especially that. So you can clearly see that there are some areas that mountainous vegetated areas that NORD has failed, but we have got quite high similarity between true and reconstructed covariance matrices. So this is the over sea surface, again, comparing those all 3 methods, residual unit, Sirius, and NORD. But I just want to highlight that over sea surface, the deep learning methodology might not work well in some scenarios because it might the reason could be that it is not realistic if we have got values below noise floor. But of course, in here, you can clearly see that the SLT values are quite low over the sea surface compared to physical-based methods. Sorry, I'm wrong. I think the NORD has been the best. For residual unit, we have got higher SLT values. So these are the key findings. So we have tested deep learning methodology. It has shown better results compared to physical methods because it can learn nonlinear relationship between true and input and output. We showed this using different indices, HLT and complex coefficient values. And why the stories and node fails because of that reflection symmetry. That we have got failed values over complex urban environments. And we have shown that the residual unit in particular has shown very high complex correlation coefficients, proving that it can preserve phase and polarimetric information, which is critical for interferometry. So the methodology itself, if you look into this feature of star emissions or the current star emissions, this is the way that we can still capture compact polarimetric star data and then get the visual quad-pol data using these deep learning techniques. So to keep the coverage as much as possible and to gain the polarimetric richness from this deep learning methodology. So this is a special issue that I'm currently running, and there are 3 only submissions that can be submitted by the end of February. If you have any interest, please submit your interesting work to this special issue. Thank you very much. I would like to thank my PhD student who planned to come here, but because she couldn't she couldn't make it, and I just presented on her behalf. Thank you very much.
Thank you, Vahid, for this presentation. Do we have questions? Yes, please. Elise.
Thank you very much for your presentation. I was wondering, have you tried to analyze where the results are significantly different between the classical methods and the deep learning methods? I have seen that, for example, on the sea, perhaps deep learning is not as useful. I don't know.
You mean this slide?
I mean the slides before on the residual errors. That depends also on the maximal intensity, I think so. For example, root mean square errors and so on. And
you mean here?
For example, and
okay.
Also on your qualitative results, I have seen that conventional methods are perhaps more noisy on the pixels where intensity is very high, and so the relative error is very high too. And my relative question is also, have you tried to analyze where all methods fail? Because
sorry,
it would be the pixels where compact pol would be useful, and perhaps you could gain insight in where are the locations where full polarimetric is useful, because I mean, if you can reconstruct full from compact, that means that compact is never useful. So my question was, could you try to use this kind of algorithms to better precise where full polarimetric could be really necessary to understand the whole physical interpretation of your signal?
Okay. I hope I understood your question. So basically, I would like to say that your first question, that why the deep learning works better than node or series. Of course, this is clear. I showed you the result over urban area because those methods rely on reflection symmetry. And it's very clear, and also there are some other, and they assume also linear relationship between input and output. So, so deep learning techniques basically they don't. They do this magically. This nonlinear mapping between input and output. So the thing is that what we have got is just based on the pixel between input and output. That we have got the covariance matrix of compact pol and the quad pol, and this residual unit, because of this residual network blocks, has worked best. But there are some issues with this technique, because we need to consider consider the physics of the data, because just they do it based on what we have fed into. We haven't fed physical information or wavelengths or the incidence angle into this, because, for example, these two scenarios I show, radiosat 2, Polinsar, they might have different incidence angles. So there are a lot of issues with this technique still that we are working, like for incidence angle ranges is one issue. Then we could have different timings, different other issues that we need to consider, especially the physics of the star data. Because what we have done is just we have fed these complex covariance matrix of compact and quad pole data to see if they can learn these differences between input and output. It has worked better, but still we are trying to look into more data set, more diversity of data set, or maybe different wavelengths or different incidence angles that can map these two. Yeah, and also different scenarios, because these are just focused on San Francisco. We already know this area.
I understand well. Perhaps I was not very clear.
Okay.
I realize the difference will be less in the case of deep learning algorithm, because the algorithm will try to minimize the differences between the intensity relative map in each channel. So I'm okay with that, but my question was more physically. It's still probable that you will find some pixels where any algorithms can predict what is the full information, because you have not the whole information in your measurement. So my question is, do you think that we will always be able to predict from compact pole, or do you think that you will find some places where full polarimetric is still necessary, even if you have algorithm to predict the most probable signal?
I think, if I understand you correctly, of course, we know the value of the compact pole data, and the major goal for this work was that to have a trade-off between polarimetric information and the coverage. For example, we have Sentinel-1, but we don't have rich polarimetric information. The main point was that if we can try to get the model as best as possible, that we can get polarimetric information from any other sensor, like Sentinel-1, or maybe, I know, for example, the NISAR is going to, has collected dual pole data in some areas and quad pole data in some areas. Can we use these models to train, and then we can reconstruct those gaps? So this was the major, I hope I answered, but if not, we can try to speak afterwards.
Thank you very much. I propose you continue this discussion during the coffee break. We need to move to the next speaker. Thank you very much.
Thank you. For the next speaker, I will not read the title, because maybe again he will take a freedom to change the program. So Armando, please.
Surprise presentation for this. It's about hairdressing. Yes. So, hello everybody again. So this is the second presentation for today. Is my last one as a first author. So this one is a little bit more, less different, a bit more mainstream, and it's about using the covariance matrix. But what I wanted to do here is to investigate a little bit more this methodology that we use for decomposing the data in two main components, so a target and a residual one, and what one works the best, and so on. So yeah, this is the long title. And the motivation again, speckle, and I can skip this. And it's also good that it's a second one, because this is even longer than the first. But let me start this. So the idea about decomposing into targets is quite old. It's probably as old as polarimetry. Was many decades ago, and it was very useful, for instance, for optical data, where people wanted to decompose into a main coherent wave, and the rest they were calling noise. So if you are thinking about the polarimetry in terms of a receiver, so then you want to really know which is the polarization of the transmitter, and when all the wobbling of the wave is noise for you. You throw it away, you go to the first one, and you get the actually what the transmitter is sending you without noise. And that was what people were doing many years ago. When we come to radar, this cannot be applied. You cannot just say, I have one target and the rest is noise. This was debunked by, I think, Shane-Claude 30 years ago, maybe. You cannot have one single target because you don't have a single wave coming at you. You are bombarded by two waves with two receivers. You cannot just say that there is one. You need to have more. Yeah. So here we don't want to say that. We don't want to do a target plus noise. No, we are not doing that, okay? This is just a target plus another target. And these two targets don't even have to be coherent. They can be incoherent as well. Okay, so there are different ways of doing it, and I was looking a little bit how people do these things. And some are data-driven, some are more model-based, and you can have using the scattering matrix, you can have using the covariance matrix. And I present here a few. So this one was proposed by Shane not long ago. So looking at orthogonal space, the reference is here. And basically you take advantage of Colpotier decomposition. So you find the main scattering mechanisms, and then you go, you separate the first one for your target and the other two for the rest. So what is left is the orthogonal space to the first target. Shane does a little bit more cleverly than just this. I do this way so that it's comparable with other, but please read this paper to know a bit better how to represent this rest. And this rest is not noise, it's signal. There may be even more information here than there. This repeats a little bit what people do in optical, where they want to find the main component of the light, see the reflection. They want to check it out and see the image without the reflections. It's a little bit coming probably from that way of thinking. The second one is what I proposed a couple of decades ago, is the polarimetric notch filter. This uses a formalism where you vectorize the covariance matrix. So you go into this 6-dimensional space with just some nice property. We can talk more about this, but this is also, this is no, so it was already known that you could do these things to a Hermitian matrix, and it's the way that you say that an Hermitian matrix, for instance, looks like a cone geometrically. So it's no out of the box. There was something before on that as well. So what it does, you set your target of interest, this normalized vector, represent your target, can be taken from the data, can be taken from your model, you choose. And then you have the rest is what is left. One point to mention, the one of Shane before, you cannot choose which one is lambda 1, is the first eigenvector. The first eigenvector is what it has in the data. It's not tunable, it comes to you. While here you can tune what you want to extract. So this is one of the main differences you'll see later. So problem of this one, you cannot really reconstruct a covariance matrix because you are in this other space, and going back to the space of the covariance matrix is a little bit tricky for the residual. I'm still working on that. So another way you could do this, and several decomposition have done this in the past implicitly, is to you consider a target like covariance matrix representing your target of interest. Say this is my volume, and then you subtract from the covariance matrix of the rest, and what comes out is your residual. It can be surface or whatever is your model about. So to formalize this a little bit better, so a little bit more generally, so that you can apply to any target you want, not just that target, the decomposition like. You can consider a target of interest with any generic C matrix, covariance matrix. You normalize it by trace, and then you do the inner product. So it's the trace of the product of the two. And what comes out is the projection. Then you multiply the projection by the vector, and you remove it. Then your powers are the traces of your target and your residual. So this is formalizing those things. But a lot of few decomposition use this kind of thing. And there is no reference for this because it's say the contribution. Another way, also, I think the the person that I know this the best coming from is Shane-Claude as well, but I think other people may have used this in the past. This is a well-known trick in algebra when you work with Hermitian matrices, and it's a way that you ensure that what you're taking out, so your residual matrix here, is positive semi-definite, so PSD, positive semi-definite. This means that the diagonal are all positive, your trace will be positive, the target is physically feasible because it doesn't have any negative power. If you have negatives on your diagonal, your target is not physically feasible because in what we do there is no negative power, such a thing as negative power. So the one before was not forcing it. This one does. How it does? There are many ways. This is a trick well known. Many ways to do this. The one that I like to talk about is the interpretation that I like to talk about is the Rayleigh quotient one. When you consider this thing, your matrix minus the target, so what you are residual, and then you force these things to be bigger than 0, and it ends up with diagonalized joint. You see, from here it's like a joint diagonalization, right? It ends up diagonalizing, doing a joint diagonalization of the two, and you go for the minimum eigenvalue. In this way, you're sure that there won't be any power there, which is smaller than 0, because you are flipping to the minimum of what you could be. And these things comes out same from here on, same as before, but these things are positive semi-definite, so they don't have negative eigenvector, negative powers. All good stuff. A reference on this, you could read this paper from Shane, and it's about, here is about change detection, but it's applying these things to differences of covariance matrices. But there's also other that you can find that do this trick. So that is the theory. Now let's see some result. Again, biomass. And again, I can skip on this. I can capitalize on the first one. And this image is the radar coordinate image of what I showed before. You see the colors are different. Why? Because here I'm normalizing each of the colors, each of the channels, over the same number, the surface scattering. In this way, the colors are really the polarimetry of the targets, and it's not a matter of visualization that you see a lot of green just because of visualization. Here, what you see is what you get. Because we are looking at how we split stuff, then I thought this is a better way of doing it, of visualizing. Although it's uglier than, say, this one, which is more beautiful. So, first things, we select a target of interest that we want to extract. In this example, I selected a target, an area, not a pixel, an area of the sea. And what I want to do, I want to strip off the image of the sea scattering. I want to get the sea scattering, so the surface scattering, not the sea scattering. The surface scattering out of all the image, but trained on the real biomass sea surfaces. Of course, the surface here is different from there. You can, if you know what is the surface here, you can train on that. So it's tunable. You just select what you want. So this we have seen before. It's the Clopot of the images. And let's have a look at the new results. So this is using the notch filter, so the 6-dimensional vector. You have the total power is here as Frobenius norm. This is not the trace, okay? It's the length of that vector. And then you have this is the target power. When you select the surface, you see it does quite well. So that vector overlaps quite well over almost all the image, and this is the complement, the orthogonal space of that one, so what is left. And there is not much, you start detecting stuff inside the, like this double bounce here. It's almost like an anomaly detector, and this was proposed as a ship detector to detect anomalies over the sea. So it does that job pretty well, but you cannot really extract a covariance matrix for your residual because you are in another space, you are in 6D space. These are the ones where you get a covariance matrix at the end. The first one, I boxed it because it's untunable. It's what comes from the Clopot decomposition, from the PCA of the data, the diagonalization, and it's always the same. You cannot set it. It just comes like that. First eigenvector, eigenvector, and the rest. So this is the first eigenvector, most power, this is the second one, and you see it's quite interesting, this residual space is quite interesting to look at. It's not tunable, but still quite interesting to, but it's not, again, it's not tunable. These two are the ones that you can select, and for these two, we selected a pixel in the sea, okay? So no pixel, an area. The area was around here. First, let's look at the one of the inner product, easier to see. So you just take whatever is the projection over the surface, and then you look at the rest. The sea is very well extracted. The surfaces here are very well extracted. There's some residual in the wetlands and the forest here. The issue with this is that you may have some negative power. So the dihedral here could be minus 25, can be a minus number, which is not good because it's not physically feasible. But in terms of doing the job, it does the job very well. Job of extracting the thing. While if you apply a PSD, so we force that all the elements of the diagonal must be positive, and the vector eigenvalues must be positive, then you see the extraction capability is much poorer. So there is a lot of surface scattering here over the sea, while you don't want anything. You want it to remove it. And also in this area there, when you look at forests, they are about the same, very, very similar. But when you look at this area with low entropy, there is problems. It's not very good at extracting things with low entropy. Why this happened? Because when you have a low entropy, do you remember the bunched vector in the previous presentation? You have a very oblong ellipsoid there. So assume this is what you have there, and you want to extract something similar. But because this is very long, you train in one pixel can be this, in another pixel do another area, due to irregularity, maybe a little bit different. And you want to extract this inside this, you see this vector will go outside the other ellipsoid. We punch through. When you punch through the other ellipsoid, the one that you want to extract, you get negative powers. So you will have negative for dihedral and oriented stuff. The methodology says, no, we are not going there. So what I do, I prefer to reduce the ellipsoid that I extract, but I still give you all positive values. And this is where the problem comes. So PSD, fantastic for forest. If you have a low entropy target, you may expect it will not clean it very well. Checking if these algorithms are properly extracting target and reconstructing the power after. So you go the trace of the covariance matrix and the trace after you do this extraction. And you see the difference is at 10 minus 9. So machine error. They do it very well. And especially for this one of the inner product, it does very well because I don't tamper with the negative values there. I could say if it's negative, put 0. In that case, this would be bad because I'm making power. But if you don't tamper with that, then the extraction is really good. How do they look? So this now we are looking at the residuals. Represented as Pauli RGB, to have a look more or less what we see there, what is the polarimetry of our residual. So this is the Pauli RGB for the image before tampering with it, before doing anything. And this is the Pauli RGB of the residual for the orthogonal space of chain cloud, the first one. And you see it's all red, because if you remove blue, then what is left is red. And so it's missing completely the surface cut, the first one, which is often a surface scattering. So Shane doesn't propose to use this one, I want to tell you, but as a comparison, I'll show you what is left if you don't do other things. So this starts getting more close to probably what you want to do in this representation. And the PSD first. You have a lot left over the sea and the surface scattering still, because it didn't clean it well. Over the forest, you have these mixed colors, greenish, and this is probably what you want over a forest, what you want to see. And because you remove the surface, you have a lot of reds around the wetlands, and still some residual surface there, which was not able to clean properly. And where is it? this one. This is when you will use the inner product, so no constraining for the to be PSD. And you see the XC is very well cleaned, all the surface has been stripped out, it's rootless, but there may be negative powers here for dihedral and double bound and the oriented stuff. The color of the forest, interestingly, very similar, almost the same. So the two work the same when the entropy is high. When the entropy is low is where you have a problem with PSD. Otherwise, the PSD is superior. It doesn't give you negative numbers. I think I have to be quick on this one. You can apply this as an anomaly detector in the sense that you set a target to remove around in a training window, and then you look at the residual inside there to look for the anomalies in the data, so spatial anomalies. This is the way that the PNF was used to do ship detection. Remove the C, look at what is left, and you can detect the ships. I don't know if you appreciate, but you do detect the ships quite nicely there. So remove the C, look at what is left. If the ship looks different from the C, you detect it. Again, this is cool if you just want to see at this space how much power you have there, but it's not directly comparable to the trace, so which is what we use as a power of a target, and you don't have a representation of the covariance matrix. So for the residual, same things you can do for this. Again, the same problem as before. There is no error in the estimation, but somebody can do things better than others, depending if you are interested in the feasibility. And skip through these things. You can look at anomalies in the data. It could be big trees, an area with surface. It can be, I don't know, buildings. You want to know the polarimetry of those things. And here is a concluding slide, good and bad. I leave it there, and I close it here, because I think otherwise I will be late. Thank you.
Anyone has a question, but very quick? Very quick answer also.
All right.
I may have one. Your preoccupation about the positive semi-definiteness of the matrix is because you want to provide an interpretation.
Yeah, of the residual.
Otherwise, you wouldn't.
No, indeed, indeed. If it's just signal processing, you don't care. But if you want to read it and say what it is, then it's nasty to have negative numbers there. You can put to 0, but it still is nasty. Mm-hmm. Mm-hmm.
Okay. Thank you, Armando.
Thank you.
Thank you.
And the last presentation of this session will be given online by Jayashree Poladosu from the National Remote Sensing Center of ISRO in India. So I don't know if you can hear us.
Yes.
Okay.
You're able to hear me?
Yes, we can see. We can see the screen. I don't know if you can share your presentation.
Yeah.
Oh, yeah, now we can see you. Hello.
Yes, I'm going to share. Could you able to see my screen?
No, we can see many screens, but not your presentation.
Okay, one second.
Okay, now, yes. I don't know if you can move to the presenting. Yes, okay, perfect.
Yeah.
Now we can see your presentation, so the floor is yours. Please.
Yeah. Good afternoon to everyone. Myself, PV Jayashree from Indian Space Research Organization, India. And I will be presenting on behalf of my authors, Gopi Krishna, Niharika, and Usha Sundari, about investigation of helical scattering signatures in EOS-4 polarimetric SAR data. So in this presentation, I would like to introduce about ISRO's EOS-4, which is a C-band polarimetric SAR, which is having the, basically stressing upon the helical scattering and the data sets that are considered. And in specific to covariance matrix versus the polarimetric decomposition, the impressions that we can take and the details of the targets considered, methodology, in specific to that corner reflector analysis towards the validation of the results and the conclusion. So I just want to bring out EOS-04, that is ISRO's, it's a second C-band SAR, which was launched here on now 14th February 2022, operating in the C-band with 5.4 gigahertz. And it has the capability of operating in different imaging modes, that is in the strip map, ScanSAR, and sliding spotlight. And all these modes can be operated in all the polarizations, that is single, dual, compact, and full pole, having the coverage from 10 to 223 kilometers and the spatial resolution varying from 1 meter to 50 meter. And people who can internationally, it is available, this data, and it from 23rd March 2022 onwards, and data which is 5 meter and above is freely available in Bunidhi web portal. So this the present study considers the full pole data, and there are various levels of products that are available for EOS-04, right from raw data product to the slant range and enhanced terrain georeference product, and level 2B NRB product, which is a COS endorsed product, and level 1C is the polarimetric products also, with the covariance matrix as well as a decomposed matrix available for the users. So here I have considered the EOS-4 fully polarimetric data, so which was acquired over Shadnagar, which is the one of the prime area in Hyderabad, and where we had an Calval site having the corner reflectors deployed, which has the capability to characterize from X band, C band, L and S, and even P band also. So this is the Yamaguchi polarimetric decomposed 4-component image. And the present search is for the structural asymmetry, which is possibly seen in the helical scattering, so which represents the structural chirality and the phase asymmetry, which is distinct from the other standard mechanisms like odd bounds, surface bounds, and volumetric. So this study, we have basically want to investigate whether there is any correlation between the covariance matrix as well as the power of the helical component. So whether this is the basic objective in taking up this study. So as we all know that Yamaguchi 4-component model has all the 4 components corresponding to surface, double bounds, volume, and helix. So because we are basically studying about the helix component, which has a circular polarization coupling also in this study. So for this, we have taken in a area named Shadnagar in India. So the acquisition is, we had acquisitions from 2022, 23, 24, and 25. And the project, the present area is the full polarimetric quad pole data acquired over the Shadnagar. So this is a SAR image. So where you can see all the various different features, in which specifically we have taken the calibration site so that we can use it for the validation. The targets of to address the helical scattering behavior, so we have taken the targets corresponding to the solar panels, and some having a forest phenomena as well as some urban regions. So where we have calculated for all the 9 components of the covariance matrix to specifically identify the helical property. So where we have found a strong covariance asymmetry for solar panels and the forest kind of things. And the methodology we followed was we have considered multiple area of interest of different targets, On top of those AOIs, so we have considered this zonal statistics. So based on the zonal statistics of both the covariance as well as the Yamaguchi four component parameters of especially for the helix. So we have performed the cross correlation between these two to extract the mean as well as the other other parameters for decomposed helical component as well as the covariance. So this we have done it over many data sets. So we have also done the traceability analysis, which is the mathematical link, where we observed that the direct link is from the for the strong correlation was observed with the cross polar terms, that is HH HV kind of thing, and inverse link, which is the negative correlation, which we found for surface as well as for the double bonds. So one second. So finally, this helical response is governed by the imaginary off-diagonal elements of the covariance matrix. So this is the statistical traceability and the validation we have performed. So which shows that the correlation, Pearson correlation coefficient R is around 0.82. So for the cross components of the covariance matrix versus the decomposed helix power. So the summary of what we could find out from this AOI-based zonal statistics and the correlation is that the 90 degrees, the imaginary off-diagonal elements, it will add, it will confirm the circular polarization, and it could able to give a direct connect to the imaginary part and the helix component in the decomposed image. So this correlation we could able to achieve. The same thing we verified and validated with the corner reflector, which we have deployed for EOS 04. So we had the Calval site. So the image has been acquired, and here you could see that for all the four scattering phenomena, for even, odd scattering, helical scattering, and the volume scattering. So in the even, we could able to identify the corner reflectors and also in the odd scattering, whereas in the helical and volume, so there was no response from the target from the corner reflector as expected. So the same thing here, we can see it in detail. So this is the Yamaguchi decomposed image. So here for even bounds, we have oriented the square dihedral because of its two plate nature, both perpendicular to each other. So we could able to get the response in the even scattering, and in the odd scattering we oriented uh, trihedrals. So this is as per the theoretical significance, whereas in the helical and volume there is no response from the targets. So showing that this helical component is more dominant in the cross pole component of the covariance matrix. So the same thing after doing the RGB, the red one signifies the dihedral component, as well as the blue dots represents the impulse response function of a corner reflector for the odd bound scattering. So this from this we I would like to conclude that the helical scattering observed in RSAT 1A. So based on this study, so we it is governed that covariance asymmetry is observed in the imaginary component of the covariance matrix, that is the cross pole component. So and for the copole, it is not giving a complete information about the helix component. So in this way, a strong positive correlation was observed between the helical response as well as this imaginary part of the 2-3 component with the Pearson coefficient as 0.82, so which is confirming that the covariance origin of helical scattering. So with this, the future scope, what we want to further extend is to over various feature-rich targets and we want to categorically differentiate all the scattering mechanisms deriving from intermediate covariance components, adding one or more dimensionality for the target classification. So this is the future scope, and this is a preliminary study. And these are the references, and the data products corresponding to EOS 4 are available at Bunidi. So it is free to the users throughout the all the apart from India. So people can download, because the corresponding sample products as well as the brochure and the product format document along with the processing tools are available at Bunidi. So that's all from my side. Thank you very much.
Thank you very much. We have time for questions.
Yeah.
Are there some? Yes, please.
Thank you. Hello, Jaisiri. This is Åke Rosenqvist. Hi. Very nice presentation. Thank you. I have a question just on the kind of targets that kind of result in helical backscatter. You said here, like forest canopies. So, I mean, forest canopies, I mean, is this something that you would see extensively, kind of this helix? I mean, I thought that forest canopies were dominated by volume scattering.
Yes.
But so you say that it's a mix of then volume scattering and the helical scattering in the forest. And also, second question: do you think that this is specifically for C-band, or would you expect to see this in, say, L-band data as well?
Yeah. So for the first one, we have taken the L-band, I mean, forest as well as the other structures. So we could able to find response from even the forest. As per the literature, they based on the structure of the forest, the helical component can also be available apart from the volume scattering. So this is the first one, and the second one is we haven't tried for the other bands, because of full pole data as of now we have it for the EOS 4, and for NISR S band and L band, I mean, we would like to understand how the mechanism will happen for different targets.
Excellent. Thank you very much.
Thank you.
We have time for other comments, or I may have one if I can. It's a naive question. Did you test your technique of since having a pronounced topography, so to account for the azimuthal orientation? How do you separate the two effects, I mean, the orientation and the correlation coming from this helical component?
In terms of corner reflector orientation, you are saying?
No, I mean, if you have a scene which has a very pronounced azimuthal orientation, let's say a scene with topography, you will have a natural correlation between co and cross channels. That has.
Yes.
Do you account for this in your decomposition?
No, the decomposition is the normal Yamaguchi 4-component decomposition only.
Okay.
So, which has been considered in the algorithm itself.
Okay. Okay. So my question was, could you test it on a scene where there is a pronounced orientation in azimuth to be sure that it separates correctly the two effects?
Okay. So to that level, validation has not been done. So we have done with the standard radar targets as of now. So we want to extend this in specific to the, I mean, whatever the azimuthal symmetry, as well as for the other frequencies and other, I mean, detailed targets also.
Okay, thank you. So if we don't have any additional questions, I propose to thank very much the last speaker. And we will now close this session on the...
And then we continue with methods after.
Yes, we will continue on methods just after the break, so don't leave. And there are 5 other presentations that are waiting for you. Thank you very much.
So welcome back. So welcome back on this second session of this afternoon. It's about Polinsar and Polinsar techniques for forest application. So we have forest on the moon. If you don't know, then wait for the second presentation. And we ask for Mr. Lee, the presenter of the first presentation. Ah, excellent. Miss Lee, I apologize. So you introduce.
So the first talk of this afternoon is from Yi-Young Lee from the Pusan National University in South Korea. And she will present the full polarimetric calibration of ground-based radar using corner reflectors. The floor is yours. It's coming. Wait.
Hello, good afternoon. I'm Jae-Young Lee from Pusan National University, Republic of Korea. Today, I will present our study on full polarimetric calibration of ground-based radar using corner reflectors. Actually, our research on the ground-based radar is still at early stage, so our processing approach is based on the work by Ferreder 2017. Building on their method, we conducted polarimetric calibration, and additionally, we applied the calibration coefficient to other datasets. First, I briefly introduce the background of polarimetric data. Full polarimetric data show different scattering response depending on polarization. This allows us to obtain information on scattering mechanisms such as soil moisture and vegetation canopy. When combined with interferometry, vertical information can also be used. This allows to obtain information on scattering mechanism, and this makes it possible to interpret the physical cause of change in nature and man-made environment. Many remote sensing studies used spaceborne pulsar data to obtain such geophysical information. However, satellite SAR systems have revisit time and fixed observation geometry. Because of this, they have some limitation for rapid local change and high temporal resolution observation like glacier and tidal flat. To overcome this limitation, ground-based radar systems have gained attention as they provide high temporal resolution and flexible observation geometry. In this study, we used the GPRI2 system developed by Gamma, and its main specifications are summarized in the table on the right. As shown in the left figure, GPRI2 consists of 6 HMV polarized antennas, which allow for polarimetric data acquisition with user-defined temporal baseline. Although the antennas are physically separated and crosstalk is expected to be small, the rotational scanning geometry and antenna spacing can cause phase imbalance and polarimetric distortion. Therefore, polarimetric calibration is essential for accurate analysis, and for this purpose, trihedral cono reflectors were installed at the calibration site, like the figure. The object of this study are as follows. First, we conducted polarimetric calibration to GPRI2 for polarimetric data at calibration site based on previous study. Second, we validate the calibration quality using cono reflector response and apply the derived calibration parameter to the other study area. Finally, we investigate the applicability of calibrated GPRI2 data to various scattering environments. The processing procedure follows the previous study, and detailed theological background can be found in the reference. Two triodal cono reflectors were used. CR1 was used for calibration, representing the blue circle, and CR2 for validation, representing the yellow circle. The processing flow is as follows. First, raw data acquisition. Second, beam squint correction. Third, azimuth page lamp removal, and polarimetric and topographic and polarimetric calibration. First, I will explain the beam squint and azimuth page issues. In GPRI2, the beam scan depending on frequency. During the chirp, the main lobe does not continuously illuminate the target. This reduces the effective bandwidth and degrades range resolutions. To correct this, we approximately the frequency-azimuth relationship using point target, estimate the parameter from the data, and apply the correction as shown in figure B. Even after this step, azimuth phase length remained, especially in the VV channel, like the red arrow in figure B. This caused by the rotational scanning geometry and the offset of the antenna phase center. We model this geometry, estimate the phase center position, and apply azimuth integration with phase compensate as shown in figure C. Next is topographic phase removal. Due to the physical baseline between polarimetric channel, topographic phase can be included in the polarimetric phase difference. If it is not corrected, HH and VV phase difference is reflectoring effect rather than scattering mechanism. In this study, we generate interferogram using HH1 and HH2 SLC like the left image, which have same polarization but different baseline. From this, we estimate the reference topographic phase like the right image and remove its scaling with polarimetric baseline ratio. Polarimetric calibration is based on a linear distortion model of scattering matrix or covariance matrix. GPRI2 measured one polarization at a time, and the antenna are physically separated. Therefore, crosstalk is reported to be very small. Also, in our data, trihedral purity was higher than 33 decibel, so we focused on the correcting co-polarization amplitude and phase imbalance and cross-pole imbalance. Our parameters were estimating using CR1, and the inverse calibration matrix was applied to obtain the calibrated covariance matrix. The calibration results obtained using CR1 were validated using the independent CR2. The copolarimetric amplitude was corrected from 1.05 to 0.99, and phase imbalance was also effectively corrected. Cross-polarimetry leakage also remained at a low level. This result confirmed that the calibration was stable and reliable, and the same calibration parameter were applied to the study area data. The study area is located in Sinan, South Korea. The red polygon indicates the observation area. It includes both flat, sand, bridge, and sea farm, and these pictures are the main land cover type in the study area. And the yellow box indicate the region used for analysis. Here we compare intensity image before and after calibration. In particular, in the HV and VH channel, the excessive intensity trend in the far range is clearly reduced, and scattering patterns become more distinguishable. Let's take a closer look at the quantitative result. In the HH and VV interferogram, the fringe pattern observed in the new range are reduced after topographic phase removal. In addition, after calibration, the proportion of pixels with coherence about 0.6 increased by about 1%, and the phase dispersion of those pixels decreased by about 30 degrees. This result indicates improved phase stability. We also examined range direction intensity normalization. The plot on the right shows intensity profile from R to R prime. Black line indicate before calibration, and red line indicate after calibration. After calibration, the excessive increase toward the far range is suppressed, while strong peak signals are preserved. This suggests that the calibration aligned channel scaling and removed range-dependent bias while preserving the scattering structure. In the azimuth direction, phase change caused by the skew and phase lamp correction are observed. The plot on the right shows phase profile from A to A prime. Along the A to A prime direction, the black line before calibration shows multiple repeating phase length between -pi to pi, whereas after calibration, the number of these lamps is slightly reduced in the red line. This reduction of systematic phase bias is expected to improve phase stability in full polarimetric interferometric processing. This slide shows Pauli and Freeman-Jordan decomposition result. The yellow polygon indicates representative land cover area. Before calibration, both decompositions show an overestimate of the volume component toward the far range. After calibration, this gradient is suppressed, and scattering characteristics become clear for each land cover type. This result is consistent with the intensity normalization and shows that calibration affects polarimetric decomposition interpretation. This slide summarizes the dominant scattering components for each land cover type using pie chart. Before calibration, volume scattering is generally overestimated, mainly due to far range effect in the data. After calibration, different scattering behavior becomes clearer depending on the land cover. For bridge area, the contribution of volume scattering decreased and double bound scattering becomes dominant, which is more constant with the expected physical structure at the bridge. For sand and mud flat, the relative contribution of surface, volume, and double scattering become more balanced, indicating a recovery of surface scattering characteristic over flat area. In the case of sea farm, a mixture of surface and volume scattering is observed. Although double band scattering is often expected in the sea farm area because of the sea surface and sea farm structure, the near horizontal observation geometry likely enhances the surface component in this dataset. Overall, these results show that polarimetric calibration changed the relative contribution of scattering components and has direct impact on the interpretation of polarimetric decomposition result. In summary, we performed full polarimetric calibration of ground-based data and applied it to individual data sets. The calibration reduced channel imbalance, range-dependent bias, and azimuth phase length, leading to improved phase stability. Also, scattering structure were largely preserved, while change in the relative contributions of scattering components were observed in the Freeman decomposition. Since the results are based on a specific observation geometry, further analysis is needed to evaluate geometry-dependent effect. Overall, these results suggest that polarimetric calibration play an important role in the reliable scattering interpretation and ground-based full polarimetric application. In future work, we plan to analyze calibration performance under various incidence angle and observation geometries, and to perform absolute calibration using RCS of dihedral and multiple corner reflectors. The left figure shows Freeman decomposition result from p-band biomass data, and the polygon indicate the same study area observed by GPRI2. Within this area, the CFAM region appears clearly in red, indicating that double bound scattering is dominant in the CFAM area at p-band. These results differ from the GPRI2 observation, and we interpret this difference as being mainly caused by different observation geometry and wavelength characteristics. These results suggest that there is a strong potential to combine biomass data with GPRI2 observation for improved interpretation of scattering metrics. The right movie shows time series intensity image acquired over 1 day. Here we can clearly observe the water level change deriving the tidal motion. We can see as the tide rises, the mudflat area or submerge first, and followed by the CFAM. Based on the calibration result presented in this study, this time series polarimetric data offer opportunities to study forest and wetland environment area in future work. That concludes my presentation, and thank you for listening.
Thank you very much. We have the time for a couple of questions. Is there any question from the room? No.
Thank you for the presentation. So, did I understood right that you assume only you channel balance, no crosstalk?
Yes.
And why?
I think the GPRS system uses physically separated antenna, so their crosstalk effect is really small. And then in our data, using the trihedral purity is 33 decibel. So I think we regret the crosstalk effect.
And what about reciprocity? If you look the HV and the VH channel, so if I go right on slide 14, they were slightly different. Now, the previous one, yes, no, next one, here. The HV and VH have slightly different levels.
The difference of the VH and HV intensity. Maybe I conducted additional study recently, but I think they have misarranged the antenna heading angle.
Okay.
Yeah, so the effect is like.
And what about the range dependency? You assumed one parameter for the whole range?
Yes.
Okay. Thank you.
Thank you.
Did you consider using corner reflector or dihedral to check a little bit the level and the distance?
We make the dihedral corner reflector, so when we acquired this data set, then we didn't have the dihedral, but now we have that, so we conducted another study.
Okay.
Yeah.
It's challenging to orientate properly, but yeah, it could be interesting to see independently the different polarizations. Okay. Thank you. Thank you very much.
So now for the next paper, we'll keep a well-known presenter for today, but we change the cosmic body. We move to the moon to speak about forests on the moon, no?
Yes, yes. So, yes, me again. This is the last time you see me for this weekend on the stage, don't worry. So, and this is not my presentation, it's the one of Poppy McVan, which is from the Royal Holloway University of London. She couldn't come here. She's a PhD student. I am the external supervisor and presenting in her behalf, but it's her work. So, again, this quite different. I bring all of you on the moon for this presentation, and we are going to use the Chandrayaan-2 data, applying quad polarimetric reasoning and trying to see if we can understand better what is going on there. So, first of all, why the moon? Well, besides being a very beautiful things in the sky that one can look at, it's also quite interesting for the future in terms of also colonization and going there. And I don't know much. I know a lot of sci-fi, but not of the real science. But I know one thing, that if there is water on the moon, then it makes it easier to build some colony there, because you don't have to import it. You readily find it there. So everybody's looking for water on the moon. More than forest is water what we need. And a place that they say there could be stuff, water, is at the poles, where there is this area which are always in shadow. There is never sun going on that area, so the water cannot evaporate and escape. If some water ends up there, it will stay there because it's always frozen, always super cold. So people are looking at the poles, and as far as I know, they already are quite confident that there is actual frozen water on the moon. And this mission wants also to answer a bit more this question, how much it is and so on. Especially they're interested in looking a little bit deeper in the regolith, in the soil there, to see if there is frozen water there. So they said, why not we send a low wavelength SAR there? And so they did. The mission is called Chandrayaan-2, and it's from ISRO, from the Indian Space Agency. And there's L and S band, fully polarimetric. Beautiful thing. So this is not compact like the one I sent before and the problem calibrating. This is quad pole, they calibrated properly. So beautiful data to use. And yet, probably I don't need to show these things. Everybody probably, I think, knows. And also, these are not images from the moon. These are images from Iceland, where they think the conditions are similar to the moon. Imagine to live there and hear somebody that say this is like the moon. So these are images on Iceland where they believe there would be something similar going on also on the moon with the lava and this kind of environments. We have quad pole. So one thing that you can do readily is to represent the data with poly decomposition, the poly RGB, quite nice, showing these single bounds, dihedral, double bounds, and also the 45-degree oriented dihedral or volume. So this is what I will show to you soon. And another things Poppy did is to apply the Clopot-Tier decomposition and looking at the eigenvalues, entropy, anisotropy, and alpha angle from these areas. One note of care when using the Chandrayaan-2 data, because they didn't have a lot of power sending down, so this is not like NISR or ALOS. It was much. This is more small scale thing. Yes, much less power. So the signal to noise ratio is not always brilliant. Sometimes it's quite low. You have a lot of noise. So if you apply all this polarimetric reasoning and you don't correct for the noise, you will think there is a lot of volume there. You may even think there are forests. So one important thing is to correct for the noise. The way that we did it is the way that I like it is 4x4 coherency matrix, go for the minimum eigenvalue, and then reconstruct an approximation of 3x3 without noise. There are other ways as well to do it. This is the way that I like. But it's important to do. You cannot skip this thing. Otherwise, you will really... it's not easy to read the polarimetric data if you don't do noise removal. So, what is the idea here? So, also this collaboration. So, Poppy wanted a way to be able to say if there is mostly surface scattering or if there is mostly volume scattering in a region. If there is mostly volume scattering, then we can look at different areas on the moon and then see are the region where we expect more water, so more inclusion of frozen water, a higher backscattering, a lower backscattering. Is there any correlation between what we see as a volume and what we expect to be as water there? Needless to say that whatever you say here, you are right, because there is no ground data. So, but there are experts, they look at the data and they say, okay, here is more reasonable to have water than there. So you still have somebody judging your work, but there is no ground data, of course. Nobody really knows how much is there in all the locations. So, coming back on why we're doing this, we want a way to separate surface scattering, or what we believe is the surface scattering on the moon, to volume scattering, and then look at the volume scattering. And we don't want to do this with the Freeman Darden or the Yamaguchi, because they're not really built for working on the moon. We want to have a bit more data-driven way. We don't really know how this volume will behave. We want to be more agnostic. We can tell a bit better what surface will be, and then we will look at what is left, and we try to understand that. So, how can you do that? Presentation that I gave before, so it's very nice that this is after. If you are just interested in power of things, you could use the notch filter, but the problem is that what comes out here is more the Frobenius energy from the matrix, is not the trace. So care has to be given when you interpret the residual, and also you cannot reconstruct the covariance matrix of the residual. You just extract them and you see if there is patterns in the image, if there are patterns. The other one, Poppy tried, is the inner product PSD. So same that I showed before. We didn't try the inner product without PSD for two reasons. One, the entropy is quite high, as I'll show you later, relatively high. And two, because she wants to interpret the residual in a physical perspective, and you don't want to have any coherency matrix with negative numbers inside. This on the diagonal. It's no good. So she applied this one. And yeah, this say again what you were saying about separating the splitting the residuals, splitting target and residuals. So the area of interest is this one, region in Cabeus. And so you see there are craters. So this, they look like domes, but I think they are more like going down than up. So there are craters, big ones, and there is also small ones. All these dots here, there are small craters. There is a tiny bit of topography too, but mostly it's flattish. But the topography of the craters is quite significant. She said that some of these may have walls of 60 degrees slope, so they are significantly presenting a slope. And so optical image on the background and SAR image on top. Here we see the HH, the HV, and also indicating some of these craters, and Pauli RGB. Again, this is visualized with all the elements of the RGB scaled on the same value, so it's very blue because the surface is dominant, but there is other things as well. And to see these things better, one can do a Clopotier. So we have the bin alpha, beta, entropy, anisotropy, and the Pauli RGB. One thing that is quite cool to see and I think got people from Royal Holloway quite excited, is that you see these like stripes in the crater and also some features there which are not really visible in optical images. The optical images, you don't see these things, but you do see them in the radar images. Believe that they may be linked to like lava tubes or this kind of stuff, and they're visible probably because we can have a bit of penetration or because the materials are different, but they are covered by some regolith on top that you don't see in optical. So this seems to be interesting, promising, to be more investigated. And I will show you, she tried this as well later. So alpha, mostly surface scattering is what you expect. Mostly you have surfaces there, but in some places you may have a bit more penetration, and then you start having things that are where the alpha goes higher. Especially in this region here, it's quite heterogeneous as well, besides the fact that the signal is low. But it's still heterogeneous as well. Also, this one are after you correct for the noise. So of course there is some noise residual there, and you cannot reconstruct things when they are not there, of course. But these are the results after removing the noise. So yeah, the first test is using the notch filter to remove what's identified as a real surface, which she didn't show, but is located in this region here on the crater. No, right. So if you remove surface and then you look at the rest in terms of power, there is very little orthogonal space. There's very little left. So mostly the PNF see mostly surface scattering, except then, or that pixel of surface scattering. Except for the areas where you have some heterogeneity, like small craters or boulders, although it's not really visible from this image. When we go looking at other decomposition, we have the first and second and third Claude-Pottier, so what we call before orthogonal space, with the game vectors. We have the Pauli 1, Pauli 2, and 3 here, and we have the tunable one in the middle. So these two columns will always be the same in my slides because they don't change, they're not tunable. This one in the middle, put in a box, is the one that changes while you tune for different things. So again, there is quite a lot in the first scattering mechanism, but also you have places where you have other mechanisms happening. And if you look at the Pauli, mostly surface, but then you have these regions here where you have also dihedral, oriented and not, or volume, that also are inside this image there. So selecting the surface, what is left is this one. And you see there is a lot on this crater here. Probably the wall was creating some double bounds. And there is a lot of these little craters which produce a scattering mechanism which is different. So this can be used to identify those locations. But also some splodges of stuff somewhere else, which doesn't look like a crater, so it's something else, probably some more volume scattering happening there. And this is when we extract things that are heterogeneous, so we train on windows around, and then we test in the windows in the middle. And here you just get the spatial anomalies. Again, quite similar to what was before, because these things are mostly anomalies. No surface is mostly anomalies in these images. So there's pretty much relatively similar to what we get before. And we get all these dots for the craters that pops up. So this is looking at the residual when we extract anomalies. So we want to extract this, what is on the background, mostly surface, and we want to look at what is inside. And these dots here have higher alpha 1 for the composition that we make. The RGB, unfortunately, is quite bad. We have to improve on that. You cannot really see much. But from the alpha, you can tell that these dots has higher alpha, so probably related to double bounces that this wall of craters were creating. And the entropy also, you see, is a bit lower than what we got before. or something that I forgot to say is that the entropy of the scene is relatively low. So it's relatively high. So that's why the PSD can be applied. I missed that on that slide. So now she selects a pixel which based on the geology of the location, should rise some volume scattering of water in it at least. And so select the pixel and then apply the same things to look at the residual. If that's really volume scattering, what we have left? Because before she did surface, and then we got the volume. Now she's doing for the volume, and what we get is what is left after that. And looking at the alpha angle there, you see we can characterize very nicely the surface, the residual, which is a surface scattering for those regions. When we go to this more heterogeneous stuff, they are mixed. There is a bit of, what is that, green, a bit of red. There's many things going on beside the volume, so probably volume. There's many volume, so many things going on after you get the volume out. So this is still to be understood, but it's nice that you see the surface when you extract that volume thing there. And then there's another one, pointing on one of these features inside the crater, these lines that you see inside the craters. And what comes out is even more surface scattering. So they are quite different from surface scattering. They're really good at removing all but surface scattering, it seems. And also the entropy of this region of the residual is very low. It's really the surface. They're picking up, the residual is really picking up the surface better than the way that we were doing it before. So at the moment, this is just preliminary results. She's starting see what we can get from the data, but more interpretation with geology has to come after this. To make sense of these results, to see if really analyzing this way is improving to detect area where we expect more ice inclusion, and then to see if there is a correlation between the power of this thing and what people expect the amount of ice inside the ground. So that is the end of my talk. Thank you.
Thank you, Armando. Questions? Stefano.
Thank you very much, Armando. It is just me being slow, but I didn't get how you define the target.
Yes.
That you.
Yeah, in this one, Poppy selected points inside the image. So take a little square and then extract the covariance matrix. That is your C target. Normalize and don't do the rest. So selecting from the scene. There is also this one where you do it locally, where instead you use a big window with a gap in the middle. You train, and then you use the middle for the test, if they are the same or not. So you look at the target is what is outside, the residual is what is inside, which is not target.
Thank you very much.
Irina? The microphone is...
Has two wavelengths, right?
Yeah.
And my question was, which one was now chosen here? This is the first.
L-band, sorry.
Okay, probably I was not aware of. Okay, L-band. Yes. And then the second question coming out here, S-band, right? Did you also check S-band? Would be interesting to see the difference, and then to see if you really see on both only surfaces, then it's clear, right, that you have nothing more. Or, you know, this could be a good indicator because the wavelengths are not so much different. Just as a suggestion.
Absolutely, indeed. We need to analyze this. I don't know if Pop is analyzing them. I will ask her. But the one that I see is only the L-band. But the S will improve. I don't know if there is problem with S. That's why she's not using it. I need to investigate more. But it's only L at the moment.
Yeah, thanks.
Armando, maybe how you can distinguish between a scatter and a noise, or a scatter and a depolarizing volume?
Okay, so yeah, at the polarizing volume depends what you define as the volume depolarizing. The noise is one that they correlate everything fully. So it's entropy one type of target where you have an identity, a scaled identity matrix. This is what one that we removed. So we went for the minimum and we removed that as an identity matrix. If you have a volume like that, then you will struggle, you will think it's noise. That was the question, right?
Looking on the image, I see this entropy increasing and decreasing also within the crater. So the positive slopes have low entropy, the negative slopes have high entropy. Is this not a SNR problem? Why should volume be on the negative slopes?
Where is the Pauli?
Whatever you go, even on the entropy map.
No. But anyway, that is true. I think there is this one. Yes, so this is the in and out of the crater, the one that faces you and the one that is not facing you. Of course, the signal to noise change a lot. Part of this entropy increase is given to that, definitely, 100%.
But it's the only place where you find a volume.
She also finds it, she says that here is it's still lower SNR, but she says that it's also there. I mean, it's expected there. But definitely the SNR is playing into that. We do the removal, but the removal is not perfect. So you correct the power, but you cannot correct the phase that you have lost. So when you do the entropy still will be low for that area.
And if you look on the anisotropy, you start to cry.
Yeah, there's nothing there. Yeah. No, this is a good point. To try to disentangle the low noise from what you believe is a volume. Yeah, it's a good point. But also, probably your volume will not be very reflective. So more like sand. It goes in like a desert. Goes in and sort of disappears. It will be dark.
And this is then
a problem.
SNR again.
Yeah, exactly. Yeah. But yeah, this is one of the things we need
and
to.
How does span data look like?
Oh, I don't know. I've never seen them. Yeah, I need to ask. But I don't know if they are. The calibration was decent. The calibration was okay. They did the calibration on the ground, use the same there. They don't do a calibration on the moon. But what you see, it looks all right. It's not too bad. Well, except the signal to noise ratio.
Any other question? So then?
Thank you very much. The next talk will be provided by Lea Albrecht from DLR, and she will talk about the multi-scale analysis of interface measurement for forest structure characterization.
Thank you.
The floor is yours.
Hello, everyone. So my name is Lea. I'm a PhD student in the Polinsar group at DLR, and today I will present you our attempt to characterize forest structure using interface measurements from TandemX. So why are we interested in forest structure at all? Of course, we all know the pivotal role that forests play for us, but that is only true if we have an undisturbed forest, because then the balance between carbon uptake and biomass losses is given. Now the problem starts when the forest gets degraded, because then somehow the carbon uptake is less than the biomass losses, and the forest gets to be a carbon source. Of course, we look at different reasons for this distortion. They can be like natural, coming from droughts or beetle infestations, but also anthropogenic reasons. So we are interested in forest structure in order to see those degradation events, to detect them early, and to accurately map carbon stocks. How can we now do this using TandemX phase center heights? So the main idea is that we look at the variations within those phase center heights. And on the left, we see less variation in the phase center heights. Then we speak of a homogeneous forest. On the other hand side, if we have a lot of variation in those phase center heights, we speak of a heterogeneous forest. Now the question is, at which scale do we actually want to estimate forest structure? On the left-hand side, you can see a very small resolution, like a 25 by 25 meter grid. And as you can already see, the pixels vary a lot from one to another. So if we look at a fine scale, the forest will always look heterogeneous. On the other hand side, if we look at a very big spatial scale, for example, 150 by 150 meter, you can already assume that there's no difference between the pixels anymore. Additionally, we have the problem that we have different drivers which will affect the scales differently. So for the small scales, we, for example, have partial logging events. They will only affect like single trees. On the other hand side, we have drivers such as topography or the weather, which will have an impact on larger scales as well. So let's go through the processing. We use the Tandem X co-SSCs. We form the interferogram, remove the flat earth. Then we have to compensate for the terrain. We divide through the vertical wave number, the capacitor, and end up with our phase center heights. And now the wavelet fun begins. So the wavelet transformation actually makes it possible for us not to have to decide on a scale, because we can look at all of the scales. The wavelet transformation can be implemented through a filter bank. So we have some low-pass and high-pass filters. And in the first step, we will just filter the one dimension with a low-pass or a high-pass filter. In the next step, we filter the second dimension, because we are working with two-dimensional images. We apply the same filters, the low-pass and the high-pass filters, and then we will end with a set of 4 subbands of those phase center heights. Now they give us the 3 different directions, like horizontal, vertical, and diagonal wavelet coefficients. But you can also see on the left, we have those approximation coefficients, F. They were 2 times low-pass filtered. That is why they are the coarse approximation of our phase center heights, and they will then be used in the second decomposition step as an input. So for the second step, we use those approximation coefficients of the last round and apply the same filter bank again. Now the only difference we make is that we upsample the filters beforehand. So if you look at the filters, they now have exactly double the length than before. And that is how we get to the coarser resolution. So we can do that again and again. Now normally the Tandem X phase center heights, I use a multi-look of 5 by 5, which will lead to an input resolution of 10 meters. So the first scale that we investigate are 10 meters, and then of course we always double the resolution, so we go to 20, 40, and so on. If we retrieve the wavelet coefficients, we can then make the squared sum to get the wavelet variance, and that is plotted here for the 5 different levels that we used. So if you look at the color bar, you can now see that we have the highest wavelet coefficients in the first level, which is also expected because there's a lot of variance on those small scales. But if we zoom out of the forest gets more and more homogeneous, which is why we have less energy coming from the coarser scales. After we retrieve the wavelet variance, we can then go one step further and calculate the wavelet entropy. The wavelet entropy is more or less the same as the Shannon entropy, and it gives us a little bit more information on how the energy is distributed across the scales. So if I have high entropy, it means that I have phase center heights variation coming from all of the scales. Now going back to this image over Rondonia, on the left we see the coherence, so it's a very forested area. Then we have the wavelet entropy in the middle. This is the total wavelet energy, so the sum of all the wavelet variance combined. And now the interesting thing is, if you look at the RGB image, so red is the first scale, green and blue are the 4th and the 5th scale, we can now see that we actually have different areas are contributing to different scales. So we actually can see that we have features we only see in some of scales, but not in all of them, which is what we wanted to do in the first place. So how can we validate those results? We're going back to Germany. The test site is Traunstein. It's a managed forest, so they are basically testing different forest techniques. And therefore, we also have different densities in the forest. So this part in the middle is an old growth forest. Then we have a young mature stand on the right-hand side, and a plantation on this part. And then if we look at the wavelet entropy and energy, we can already see that we have different levels of energy coming back that correspond to the different successional stages of this forest. So that's already something very good. And then for this part, there's always also an inventory data set available. So what you can see here now, from this inventory data set, I calculated the basal area. And if we look at the wavelet results, we can now see that we already match this basal area quite well. And then for this test site, there are already other established structural indices for the horizontal and the vertical structure. And if we correlate them at 50 and 100 meters, we can also see that we have a strong correlation. Now, the next thing I did was to apply it on a large scale. The test site is now Rondônia in Brazil. Why are we interested in Rondônia? Well, as you can already see, it's been part of very, very big deforestation strategies. Of course, you can also see some forest reserves. They are still protected under the government. But the problem is in Rondônia that over the last 40 years, they had, starting with a forest cover of 90%, they now only have 60%. So they already destroyed 30% of the forest cover. And another problem here is not just the deforestation, but also the fragmentation. Rondônia has now around 80,000 fragmented patches of forest, and they have problems with edge effects, so the probability for disturbances are higher, and also the biodiversity gets degraded. Now, just looking at forest height actually only tells half of the story, because when we now look at the forest structure, we see that we have different structural components playing together in this forest. This is the total wavelet energy. And now so this is a mosaic of around 4,000 different tandem X images, but we did not process only one epoch, but 2 epochs, which basically then means we can also have a look at the structure change. And for this tile, of course, in blue, we see the decreased variability, which means in this case that those areas also have been deforested. But the interesting part is now those reddish areas, because Brazil actually enforced a law in order to protect rivers and the buffer zones around it, in order to protect biodiversity. And those are exactly the river zones and the buffers around it. They get now, so they are not allowed to use management techniques in those areas anymore, so they are now undisturbed forests, and therefore the entropy increases again. Yes. So to sum up, in order to characterize structure, we have to look at different temporal scales. When we use tandem X, we can do that because it's a very sensitive data set which offers a high spatial resolution. Now we can apply the wavelet transformation in order to characterize the structure. And as an outlook, of course, when we have structure and height together, we can map the biomass on a global scale. Thank you very much.
Thank you very much. Are there some questions from the audience? Okay, maybe I can start. When you say the entropy is increasing, you mean the forest is regrowing, right?
Yes. Because a lot of those areas they used before as plantations.
Okay, and for your test site in Germany, you used one date, or did you try some more extreme dates to see if you were having also experiencing regrowth or increasing or decreasing of entropy?
At the moment, we just used one date because we want to make sure that the LiDAR measurement was taken in the same time frame in order to be able to compare those.
Is there another question from the audience?
Hello, thank you for the presentation. If I understood correctly, you've tested your method only in Germany, right? And then you apply it and was developed in Brazil. So how do you expect that are going to be the limitations in terms of the performance when you apply it in a forest that is completely, the structure of the dense tropical forest that we have there is different from the ones that we have in Germany? And a second question would be, in terms of that you believe that the structure is more heterogeneous now, nearby the rivers, does it mean that the rivers are necessarily more heterogeneous, or how did you detect the change to say that this is a result of the enforcement of a new law?
Okay, thank you for the question. For the first question, I don't really see a problem. So, of course, Froschheim is a temperate forest, and then we move to tropical forests, but we are still looking at the face center height change or the variability within them. So, I think it's valid to just move from one type of forest to another, because also it wouldn't be really possible to validate over this whole area of Rhodonia, right? That's why we had to move to a smaller field of interest where we had all kinds of data sets in order to be able to compare our results. And for your second question, I forgot it, I'm sorry.
It's just about the structure that you believe that you have major changes because of law enforcement, but changes, they come, you have to compare time 1 and time 0 to say that there was a change. And not that they're just changes because the landscape and the structure of the forest nearby rivers are different from what we call terra firme, which is the areas far from the rivers. Right.
So I think that the areas around the rivers are naturally more heterogeneous because there's less stress of the plants for water, for example. That's also why those areas are more biodiverse. And I think Rhodonia actually saw that in order, so they enforced the law in order to protect those areas, especially because they offer this high biodiversity and structural complexity.
Okay, thank you.
You're welcome.
Thank you very much.
So we stay on forest, we stay on earth, and we stay on disturbance. We change only the frequency and we move from X band to C band. And it's about a disturbance detector based on Sentinel-1 polarimetric diversity.
Hello, everyone. Thank you all for joining this presentation. My name is Marta Bottani. I'm a postdoctoral researcher at CESBio and ISRO in Toulouse, France. And the title of my presentation today is Exploiting Sentinel-1 Polarimetric Diversity for Near Real-Time Forest Loss Monitoring Using a Bayesian Detector. So let me start with some context. So forests worldwide are undergoing significant transformations. In just 20 years, about 100 million hectares of tropical forests were lost to deforestation. And to put this into perspective, this roughly compares to 50 times the size of Slovenia. And what is even more alarming in this context is that about 50% of this deforestation is actually attributed to illegal practices that contribute for about 1.5 gigatons of CO2 emissions every year. So historically, the monitoring of tropical deforestation has relied on some operational systems, such as GLAD, which exploits multispectral imagery. However, the use of optical data in tropical regions is obviously hampered by the presence of clouds. So in the same context, we have that other operational systems exist nowadays. Those are based on the processing of star imagery, for example, Sentinel-1 products. Sentinel-1 operates at C-band, as everybody knows. It is characterized by a high revisit frequency, a 20-meter spatial resolution, and it provides dual polarization second-order backscatter estimates that we denote gamma naught VH and VV. So here, if we're looking at this temporal evolution of the backscatter signal, you can see a pronounced drop, and this is typically associated with a deforestation event. And so the existing systems that process SAR imagery in this context, they try to identify over time this drop by basically using some moving average estimation followed by some sort of threshold. However, this kind of approach, of course, has some limitations. First of all, linked to the presence of speckle, which typically requires speckle filtering techniques that in turn reduce the spatial resolution of the measurements. Of course, they also struggle to handle seasonality within the time series, and they're either based on single polarization information or they typically combine dual polarization information in post-processing, which, depending on the case, can lead to increased false alarms or omissions of deforestation events. So in this context, the objective of this work was to generalize a Bayesian online change point detection framework that was previously developed to unfiltered dual polarization Sentinel-1 time series. Specifically, this approach fully leverages polarimetric diversity, and so it has the potential to detect a wider range of deforestation practices. So this is how I decided to structure the remainder of the presentation. I will first introduce the PolBioCD method. I will then briefly talk about reference data used for validation, and then we will move on to results, both in terms of deforestation detection results, and also I would like to present some results about the detection of fire-induced forest loss, and finally I will conclude with some final remarks. So the Bayesian method developed in this work for the near real-time detection of deforestation is based on an unsupervised Bayesian online change point detection framework, which basically computes a recursive online maximum a posteriori estimation of deforestation events. The starting assumption is that we have a Sentinel-1 single pixel unfiltered time series where each element of the series contains dual polarization backscatter estimates expressed on a logarithmic scale. As you can see on the right, this time series is partitioned by change points, and the objective of the algorithm is to split this time series into a set of connected segments by tracking the posterior distribution over the most recent change point. So in other words, what we want to estimate is the so-called run length, RT, which represents the number of data points since the last change point occurred. The run length for us, it's a random variable, as you can see, associated with the hidden state of a Markov model, and its processing is conducted in a message passing manner. So at each time step, we have that the run length can increase by 1, this corresponds to a growth phase, or it can drop to 0 in case of a change point, and ultimately, the identification of deforestation events is always linked to a shift downward in the position of the maximum value within this matrix. So in practice, the algorithm aims at tracking this quantity, which is the posterior distribution over the run length. If we apply conditional independence, we can write the joint distribution that appears here in this recursive form. And the computation depends on 3 elements, essentially. We have the message from the previous iteration, the prior probability of a transition that we can consider constant for simplicity. And finally, we have the posterior predictive distribution, which in general depends on the branch of the run length matrix on which we are placed. So how do we compute this posterior predictive distribution? If we assume that the data follow a specific likelihood distribution between change points, then the Bayesian approach models the parameters of the likelihood with a prior distribution. In this context, the posterior predictive can be expressed in this integral form that you see over here, but however, this is quite complex, so not suitable for near real-time applications. What we can do in this case, a possible solution would be the use of conjugate priors, which means basically that the prior on the parameters and the posterior on the parameters follow the same type of distribution that depends on a set of parameters eta, and this implies that the posterior predictive that we're trying to determine at this stage will share the same set of parameters eta. So at each iteration, we just substitute the computation of the integral with a simple parameter update. So in practice, Sentinel-1 RTC log intensity data can be assumed to follow a bivariate normal distribution. So in this case, the parameter prior, it's a normal inverse Wishart distribution. And in this context, we can derive a closed form expression for the posterior predictive, which corresponds to a bivariate T distribution. However, if we use this kind of modeling, we have to keep in mind that the empirical estimations of the precision matrix, T over here, basically converge slowly towards a diagonal form, which essentially means that we always consider a sort of degree of correlation in between the polarimetric channels. In this context, however, if we compute the polarimetric correlation coefficient raw in between the two polarimetric channels and for different undisturbed forested areas, we can see a general lack of correlation, which implies a diagonal precision matrix. And specifically, this property is called the reflection symmetry, and we want to take this into account when we deal with the change detection process. So in order to do that, we simply factorize the likelihood of the two polarimetric channels in between change points. And in this context, we have that the posterior predictive distribution becomes the product of two univariate t distributions. Now, how do we detect a change at instant t? At instant t, we can determine the most probable run length, that is denoted mt, which is the value of RT that maximizes the posterior probability. As you can see, this quantity grows linearly over time in case of no change point. And if instead we have a change, then this quantity will drop, and the value to which it drops specifically depends on the detection delay. And practically, we always apply a threshold when computing a detection. So now that we discussed the algorithm in detail, this is an example of detection conducted with the PolBioCD algorithm on a single pixel time series. As I mentioned earlier, the algorithm is recursive, so it allows us to detect deforestation events that manifest as a sort of persistent change, even in presence of seasonality. And as I mentioned also, we always detect a change or a deforestation event when we have a drop in the position of the maximum value within the matrix. So for validation, we conducted a campaign focused on two biomes in Brazil. The first is the Amazon, which is already very well monitored by existing solutions. And the second is the Cerrado, which is a woodland savanna that is under-monitored due to a strong seasonality. For reference data, we're using the Map Biomass Alerta reference dataset. We focus on the monitoring year 2020, and the principle of detection for us is based on the overlap between polygons. So if a detected area overlaps with the reference polygon by at least a specified threshold that we call T-poly, then for us that would be a detection. And lastly, we compare our results with some existing methods, which are GLAD-L based on Landsat imagery and RAD based on Sentinel-1. One step further from the actual Map Biomass Alerta 2020 dataset, we derived two sub-reference datasets per biome. The first one is including small deforested areas, so the class A0, and the second includes larger deforested areas, so the class A1, which are selected through stratified sampling. And this allowed us to map 27,000 hectares overall in between the two biomes. So in terms of results, these are for the Amazon. On the left side of the matrix, you see, of the table, you see the performance for smaller deforested areas, and on the right, you see the performance for larger deforested areas. The performance are reported in terms of F1 score, which represents a sort of balance between detections and false alarms, and for a detection threshold of 75%. So if we compare PolBioCD with VH-BioCD, which is BioCD using cross-polarization only, we obtain a 12% increase in deforestation detection performance for larger areas with respect to smaller areas where the performance are comparable. If we compare against RAD instead, we obtain 29% increase in detection performance over the smaller areas compared to the bigger ones where the performance are comparable. Instead, in the Cerrado, we have an opposite trend. So we obtain 9% increase in detection performance when dealing with BioCD versus VH-BioCD for smaller deforested areas. And we have comparable results in the other case. And comparing against GLAD, we have an overall 30% increase in detection performance in both categories. So now to interpret these kind of contrasting results, we can think about the different deforestation practices between the two biomes. So in the Amazon, typically the bigger parcels are deforested. The vegetation is left on the ground to dry, and then it is burned at the end of the dry season, so several months later. Instead, the smaller parcels are obviously cleared more rapidly. And in the Cerrado, we have that the big parcels are associated with soybean plantations, so they are cleared mechanically, and the smaller ones are mostly linked to subsistence farming, so they are cleared in a more artisanal manner. So in this context, we have that our algorithm is able to achieve a 10% increase in deforestation detection performance over areas likely characterized by post-clearing debris. And this is because after deforestation occurs and the vegetation is left on the ground, we still have a strong volume scattering component that likely saturates the signal, especially in cross-polarization. So now allow me to change a little bit subject. I would like to present some results concerning the detection of fire-induced forest loss obtained using the PolBioCD algorithm. This work was motivated by the availability of some field-validated reference data that I was able to personally collect in Brazil. And this gave us the idea to test the algorithm for this new application and also test the complementarity with multispectral imagery. So here we are in Paragominas in the state of Pará, eastern Brazilian Amazon, and what you see on the background is the start of a forest fire that took place between September and November 2024. The fire was articulated in 2 burning episodes, and overall it burned about 105 hectares of primary forest within the Amazon. The fire was started by some local farmers, and unfortunately it escaped all the controls due to the extremely dry condition of the forest at the time and some very strong winds that picked up. So here on the left you see the fire timeline before the start of the heavy rains mid-December, and on the right you see the PlanetScope mosaic relative to November 2024, which delineates the burn scar. As input data, we're using Sentinel-1A reflectivity in both polarizations and also Sentinel-2 derived difference normalized burn ratio. And I would like to point out that over the time spent covering the fires, we only had available 6 Sentinel-1A images and 2 cloud-free Sentinel-2 images. So it's a quite restricted input data set. And now in terms of results, on the left you see spatial results, on the right you see temporal results. So for what concerns spatial results, we can see an overall good agreement in between the 2 assessments. However, with PolBioCD, we identify some agricultural parcels that were actually cleared prior to the start of the fires that are correctly not mapped in the Sentinel-2 based assessment. And instead, if we look at temporal results, we can see a continuous assessment of the fire-induced forest loss thanks to the PolBioCD detections. And instead, with Sentinel-2, we're obviously impaired by the presence of clouds. So we're able to assess performance just twice. So to summarize here, we have that with Sentinel-1, we obtained continuous monitoring, and with Sentinel-2, we're able to discriminate the type of change. So we wanted to fully take advantage of this property, and we did this by creating this map that is a continuous assessment of the fire-induced forest loss for the Paragominas fires, obtained with PolBioCD detections and refined with Sentinel-2 to exclude, obviously, the non-fire-related events. Over this map, we obtain an 88% accuracy for the first fire, that is the one mapped in the middle in orange. And of course, we have lower accuracy for the second fire, the one in red, because we really had not many Sentinel-1 images available before the start of the rainy season. So to conclude, in this work, we presented and we proposed an extension of the BioCD framework to dual polarization Sentinel-1 images. With PolBioCD, we achieved a 10% increase in detection performance over areas likely characterized by post-clearing debris, and also better results compared to existing techniques. And we also demonstrated the potential to monitor other kinds of applications, such as forest degradation. In terms of perspectives, we're currently working on the generalization of the method to multi-source asynchronous time series. We have some results concerning the fusion of Sentinel-1 and Sentinel-2. I have a poster about this if someone is interested, and that also, let's say, investigates the complementarity with the Biomass mission. And for the future, we would like to include within the processing chain also some multi-frequency, for example, from NASA time series. Again. Here I included some references about the work that I just presented. I'm happy to take any questions, and I thank you very much for your attention.
Thank you, Marta. Questions?
First of all, congratulations, and thanks for the presentation. I would like to have a question, specifically when you said that you would like to extend a BioCD. If I got it well, you started with the assumption that you are using an HMM in the beginning, a hidden Markov model. Are you thinking to go, because I mean, I don't know if you are using the instant moment of the past. Are you working also to do it probably with a recurrent neural network, so to keep the history and to train the model in order to increase the results in the finale this one, and also if there are possibilities probably to extend it from the perspective of graphs, because as you are generating the HMM, probably because it is very well established, if you're going to change also the algorithm and to move to an optimization in a matter of the graph for the statistics in the end. Okay, I know it's about the algorithm, but the possible comparisons and probably increasing in the accuracy could happen. I don't know if this is in the future, let's say, aspects.
I'm not sure I get the question. So you're asking me about like the integration of multiple data sources?
Yes, in the beginning that you start the presentation, you show how you are building the probabilities by using the HMM algorithm. If you are thinking in the extension of this model to change from the HMM that, let's say, develop the time series to another algorithm as the recurrent neural networks that probably could catch more of the history of the observation and could lead you to even better results, let's say.
Okay, I think I got the question. So in short, no, I did not consider the moving to another algorithm. And there's a few, especially not like something related to deep learning. And there is like the simple, there's a few reasons, but like, first of all, like, we use an unsupervised model, so we're able to kind of adapt as time goes by to, let's say, anomalous events. For example, in a season in which it was very dry, or like a season in which it was very rainy. That is something that we would not really be able to do with like a supervised model, since we would need to train over both space and time for this kind of application. And in terms of like if I got the question correctly, like in terms of like data intensity and the fact that we need to keep in mind the history.
Exactly.
So we do not, like when the time series becomes really long, of course we need to have some information about the past, but we can, after a certain amount of images, we can, let's say, exclude from our processing the least probable run lengths, which basically is the equivalent to limiting the stack and not having let's say, a matrix that grows to infinity.
So you know already how to cut.
Yes, we can limit it operationally, like this has potential for operationality, it's not operational yet, but we have implemented some limitation of the stack to not deal with, let's say, matrices that are huge in dimension.
Okay, thanks a lot.
One more question over there.
First of all, thanks for the presentation. Beautiful, really a very nice start, also good work. The question is about seasonality. Does the seasonality in some cases broke your breakpoint analysis, or you see there is no problem with that? And what happens if you have a rogue event, like a really, really big cloud, so your backscattering drops down? Is this a problem for your analysis or not?
This is a very good question. It's not a problem in the sense that, like, since the algorithm is recursive, as I briefly mentioned, in order to detect the change, this needs to appear as a sort of persistent change over time. I mean, 2 to 3 acquisitions, which makes it also quite robust to, let's say, anomalous events, for example, rain cells. We have experienced something like that. We also have experienced when fusing Sentinel-1 and Sentinel-2, for example. Sometimes we mask, of course, in Sentinel-2 the clouds, but we have some residual shadow that like drops the value of our time series. If it's a single point outlier, it's very robust to that, and we're not gonna misdetect the change. If seasonality is periodical, it handles it quite well. And as I said, it breaks when there is this persistent change over time.
And you do this only for forest, right? You first mask forest, and then you apply the detection masks.
Yes, because basically the reference data that we're using are about forest. So it's exactly where we know that there was deforestation, we try to detect it. So it's only forest.
Other question? No.
Okay.
Maybe I missed it. What was the resolution? How many look? What was the resolution?
So we're using RTC data, so we're about 4.5 looks.
4.5.
We don't use any speckle filtering.
And were you sensitive to, for example, RFIs or rain, for example?
No, as I was mentioning, when there's rain cells, it's a single outlier in the time series, so it just is like it doesn't see it.
Okay, we verify the same. You would have only one.
Exactly the same.
Okay. Second thought.
Yes, yeah, thank you very much. Just kind of linking on to the same question. I mean, a rain cell I understand, because I mean that's just like a single image kind of drop. But I mean during the rainy season, then you will have kind of severely kind of affected the contrast between forest and non-forest. So then I mean you would have a slightly different characteristics of the kind of the non-forested areas. So then you would have, I mean, kind of during several months, you would have a slightly different backscatter kind of characteristics than you would have during the dry season. So is that kind of a problem in the algorithm?
So for what we observed, if the change is gradual, so it occurs over multiple acquisitions and affects, let's say, in a uniform way the whole time series, it's quite robust to that. Of course, there could be, I assume, some cases in which, of course, if there is what I was mentioning, a persistent change over the time series, it will detect it, and if it wasn't deforestation, that would be a false alarm.
Okay.
But it's quite, for the performance that we observed is quite robust to false alarms.
Okay, thank you.
Thank you.
Thank you.
Okay, thank you very much.
Thank you.
For the last presentation of the day, we'll go to 3 dimensions with tomography and using even multi-frequencies and LiDAR measurement. So it's Matteo Paradini presenting it.
So, hello.
From DLR.
Yes, I'm presenting this work on behalf of Desiree Murgia. So she was a student, a master student at DLR until not long ago. And so she was coming from the University of Pisa, and of course she was used to present her results to her 3 supervisors, which are here at DLR and the University of Pisa. So 3 supervisors is quite an important number. But I will try today to present the same work as good as she would do. So we speak about, as a general framework, we speak about estimating 3D forest structure. 3D forest structure for me, it's something that tells you how heterogeneously are distributed the vegetation elements within a certain volume, unit of volume. And let's say so, there are for sure LiDAR and SAR systems that can give you this information because they are sensitive to the 3D distribution of these vegetation elements, but in terms of their backscattering contribution to the total backscattering. And there are, in particular, let's say so, it's quite understood that if you like to characterize 3D structure, so this is an intrinsically multi-frequency problem, because different frequencies, they are sensitive to different vegetation elements of different sizes. But in this sense, if you have data different frequencies, they have a complementary information content. On the other hand, the problem is now if you like to start to combine the information from these different frequencies, at the moment, it's not understood how to do this. And the problem is because there is no electromagnetic model. There is no electromagnetic model that can transfer 3D reflectivity profile from the one frequency to the other with the desired accuracy and especially for a quite wide range of frequencies. So in this sense, of course, you can also try statistical. You can also try statistical approaches, but you have to take into account that different sensors provide you with different measurements at different resolutions and with different characteristics. And here you have an examples or 4 examples of LiDAR and SAR sensor, which are now in space and acquiring data at the same time, and all of them can provide you something for mapping forests. So you have JEDI JEDA is a LiDAR sensors and measure full waveforms, so it measures profiles. You have tandem mix. Tandem mix, you measure coherences, interferometric coherence at X-band. So then you have, recently there is NISAR. NISAR has, or at least there is no planned non-zero based on interferometry, but the power of NISAR is that it gives you time. And then there is also biomass. Biomass actually gives you everything. Biomass can measure coherences, biomass can measure profiles, biomass gives you also access to changes. Now the question is, how can we combine the information from those? And so we have no models, we have to try something which is data-driven. So maybe speaking about data, we take airborne data from the AFRISAR 2016 campaign in Gabon. You see here you have this is the Monda test sites, this is a P-band Pauli, and you have basically a transition from a secondary younger forest up to a more homogeneous and primary mature forest. And you see also this from the profiles. We had LiDAR data. These are LiDAR acquired from the NASA Elvis instrument. And so these are the profiles, the waveforms that you get. And here below you also have the tomographic profiles at P-band. And just by looking at the profiles, you see already that so they are similar, but they are also very different. You see here, while the LiDAR tends to give you a structure or structure gradients which are mostly related to the distribution of the elements close to the top, P-band has, of course, a much larger penetration down to the ground, and therefore you have a larger vertical information. Now, to try to combine these two, we use an approach, or we try, so the task of Desiree was to try to see how far she could go with polarization coherence tomography, and in particular with the concept of taking the profile, a reflectivity profile, and try to decompose this profile in terms of basis functions. And so in principle, you fix the basis, you have the profile. You measure the profile, you fix the basis, and then you can calculate the coefficients that allows you by means of a linear reconstruction to get back your profile. So let's say so there are several reasons why it might be worth to investigate this approach. First of all, because it's easy, relatively easy, and then everything boils down to a linear inversion. Secondly, because you can apply it directly to profiles, just like this, but you can also apply it to interferometric coherences. So in the end, the relationship between a profile and interferometric coherence is a Fourier relationship, so it's something that you can also write down manually. And because the choice of the profile basically drives the interpretation of the coefficients. So this means you can also try to reconstruct profiles with different bases, and you can also here have different bases as a function of frequency. Indeed. So how to get a basis? That's, I think, maybe I guess the first problem that you have to face. Now here we start from profiles. So we take all the profiles, we stack them together in a matrix, and then we calculate the covariance matrix. From this covariance matrix, we calculate eigenvalues and eigenvectors, and we say my basis is in the eigenvectors. And essentially, the eigenvalues tells you how dominant are these eigenvectors, so how dominant are the different basis functions in that ensemble of profiles from where you started. And the idea is that the eigenvalues which are larger, so these leading eigenvalues, can capture the dominant signal structure with minimal reconstruction error. So this means you hope that, or you have a basis to say that you can reconstruct the profile from where you start just with a low number of functions. So then we took the tomographic profiles at P-band. So we just took the AFRISAR data, calculated Kapon profiles. The tomographic algorithm in this sense are just a secondary importance, but we calculated with these Kapon profiles, and then we applied the procedure before to get the basis, and then we do the same also for the LiDAR Elvis profiles. And then these are the functions that we got. So you have the first function, this is the dominant one at P-band and at L-band, the second function, and then third, fourth, fifth, etc. And then what you see that the information content, which is mostly related to the frequency, is in the first functions. And then in the moment that you start to increase the order, you just increase, if you like, the spatial frequency or the resolution at which you get your profile. But if you like to capture the frequency information, then you have to work with the first profiles. So let's make an example. So this is what you see here with a dashed line is a P-band profile. And then Desiree took the P-band basis and tried to reconstruct this P-band profile with the P-band basis. And then she started, so she takes the dominant function, and then she adds functions. And then by adding functions, you see that already by adding one function, you already get the shape of this profile. So you don't need to go very far away. And of course, you can add, you add, and then in the end, you get exactly that profile. And then the question is, so Desiree took this basis that she found, and she basically did this game. She did this game to all the profiles that she had, and she liked to see, for instance, how good were this profile. And here you find another problem. The second problem, if you like, is there is no definition of how good is a profile. So or you know the profile, and then you just take the difference of the two profiles, but already to understand from a simple difference how good the profile is for other applications, this is maybe not so straightforward. And therefore, we decided to map 3 parameters of the reconstructed profile. For instance, we said, so normally the volume has one peak. Let's map the height of the peak. So the height of the peak, this is what you have at P-band. Now you apply the P-band basis. By applying the P-band basis, with just one function more than the dominant function, you find this variability, but just by adding one function more, so for a total of 3 functions, you have now this spatial variability, which is close to the one that you would get from the original profile. A second parameter of interest is maybe the amplitude of the peak of the volume, and as you see that, again, same story as above, with just one or two function more than the dominant one, you get this spatial variation, and also the power of the ground, same story. So you see a low number of profiles, a low number of basis functions, and you can get basically the characteristics of your profile for a wide area. Now, next game we take the same LiDAR profile, but now we use the same P-band profile, but now we use the LiDAR basis. So we take the functions from the LiDAR profiles, and we try to use those functions to reconstruct the P-band profile. And you see that now you start to struggle. So with just 1 or 2 functions more than the dominant one, you still have quite a non-negligible error. And the most of your error is here at the ground, but even here in the canopy, so you see that it's difficult with a low number of functions to reconstruct something meaningful. Now, of course, you can make the same. Also, the question is the difference that you still have, what it means. The difference means for us that maybe because you are, you take the P-band profile, you project on a LiDAR basis, but then you are taking the information which is common between P-band and LiDAR. And then this is maybe you are starting to reconstruct a LiDAR information. And this is just because you change the function basis. And indeed now, if you calculate the same 3 parameters for the profiles. And you get it, so this is what you would get from the LiDAR. Now you take the P-band profiles, you apply the LiDAR basis, and you reconstruct these 3 parameters. And for instance, now you start to see that you have something which is close to the LiDAR. Still, there is some difference. The main I think the largest difference is at the ground, of course, because they are data which they have a different penetration, and so the residual main difference is at the ground. So now let's make the case in which we don't have profiles anymore, but we have coherences. So you have a function of profiles, but you measure coherences. So from this coherence that you measure, you like to reconstruct profiles. Again, you apply the same concept, PCT, you have the basis. What you have, you measure the coherence. The coherence is linked to the profile by means of this Fourier transform. So, but if you take now the reflectivity in the Fourier transform, you express it as a function of the coefficients, then you plug everything back, and then you can express this relationship as a function of the coefficients. You just invert it. It's a linear system of equation, and you get your coefficients. The important note is that all this inversion depend on this number, this kV, which is the product between kz, so the vertical wave number, which is given by the baseline, and the height of the volume. So let's try to see now. This is, for instance, are the coherences that you would measure from the P-band data as a function of kV. So you take all the profiles, you calculate the kV, and then you make just a histogram of the coherence as a function of kV. And you see that the coherence drop for kV increasing. kV increasing means or height increasing, or baseline getting larger, or both at the same time. And now you see the coherence drop, and then at some point it comes back, it bounces back. This bounce here is pretty large because you have the ground. So you can imagine you have a main contribution which is somewhere in the ground, a main contribution somewhere in the ground, a main contribution somewhere in the volume, and then it's like you can always approximate it like 2 Dirac deltas, and with some attenuation, and then of course gives you this shape. Now, if you apply the functions, so these are how the function looks like in terms of coherences. They are not exactly coherences, but this is what you get when you take the basis function, you make the Fourier transform reverse. So you see that every function basically allows you to reconstruct a portion of this histogram. Now you can attempt a single baseline reconstruction. So you take the coherences, you apply the basis, you get the coefficients. From the coefficients, you get the profile. From the profile, now you can estimate back the coherence. And therefore, for you now, so the profile is well reconstructed when you can reconstruct the same behavior of coherence. And you see here that you are not exactly the same, but you get close. So in principle, you get the same bouncing back. You can also apply a dual baseline reconstruction, and the dual baseline reconstruction gives you something like this. So in this sense, it's not so different from before. What is important to say here that for doing this game, you need quite large baselines because you need to capture also the kV for this case here to be able to reconstruct the ground. In terms of profile parameters, so now if in terms of reconstructed coherence you were getting more or less the same, in terms of reconstructed parameters, of course having dual baseline data makes some differences, but now you try to reconstruct P-band profiles with P-band coherences and a P-band basis, and you get more or less the parameters that you would get. There is a bit of uncertainty, for instance, here in the phase center, but this is fine. So you can always think that maybe you can add one baseline more and get something more accurate. What happens now if we use the LiDAR basis? If we use the LiDAR basis, just long story short, now in this case, so you apply the LiDAR basis to the P-band coherences. So you are not able to reconstruct the P-band coherences. But you know why? Because you take the LiDAR basis, you take the first function where you have the most difference because of the frequency, and therefore This means that this difference is because you are trying now to access LiDAR information using the P-band measurements. And indeed, if you go now with the profile parameters, you see now, so you reconstruct the height here of the peak of the canopy, you reconstruct quite well, if you like, in terms at least of spatial variation, the amplitude of the canopy. You also have almost no problem to reconstruct the amplitude of the ground. So, and this was the last experiment, but to conclude, so of course you can reconstruct your profile with a few basis functions, and this is something that you like to have because this is helpful in already within the biomass mission. So if not in the tomographic phase, at least in the interferometric phase, you can still access profiles. The only problem, you have to take care of the baselines. You need a quite long baselines to be able to have a certain performance. But I think the main conclusion is that indeed playing with function, you start to transfer vertical reflectivity information with one reflectivity to the other, from one frequency to the other, and indeed maybe this is a way that we can exploit now to make all these missions speak together. And yeah, so I have nothing else to say. Thank you very much.
Thank you, Matteo. Is there any question from the audience?
Thank you for a very excellent presentation. My question is very short. Your basis functions that you use for different bands, P-band and the others, is it first, is it sensor dependent, that number of the basis functions that you need to model your vertical structure? For example, for P-band you need 3 basis functions, for L-band and others. And is it also area dependent, that for different forest types you need to model it with 3 basis functions and so on?
So for sure it will depend, or there will be some dependence. So if we speak about forest types, or at least forests with different reflectivity profile, with different dominant reflectivity profile. So in that case, you will need a basis that is able to capture the differences, or one basis or more basis function. So you are not necessarily constrained to use one. That's about this question. For the rest, of course, your basis will depend on the frequency. What we see is making this trick of taking the eigenvectors, you always tend to end up independent, this, at least in the experiments that we did, you always end up to using then tutoring functions. So, but in general, I would say that you will always find yourself to work with a low number of functions.
Thank you very much.
There's another question.
Thank you. Matteo, if I understood correctly, your reconstruction works better when you use the coherence with respect to the profile or reflectivity. Can you explain me why?
That's a good question. We also saw this, and at the moment we don't have an answer, to tell you the truth. So, and it's something that remains still open. Of course, there is the working better or working less better. It's always to be projected on the way in which you measure your performance.
I want to ask Professor that how did you propose the K1 and to the K10 profiles? Did you, yes, that's the question.
So you mean the wave numbers?
No, the profile, the K1, K10. Different.
Let's go back.
I mean, the different bases.
The different bases. We just took.
How did you propose it?
So this we just took profiles from the data. From the data, yes, and then we just make this sort of principal component analysis.
Or totally from different pixel data?
From different pixels, yes.
Okay, thank you. Thank you.
From observations. Okay, thank you very much. Before, so to close to announcement, first there is a cocktail outside with some drink, food to celebrate SAR, polarimetry, interferometry, and tomography. And second thing is to complement the announcement about the poster. The list of posters were not printed yet. They will be printed tomorrow morning. If you already want to pin your poster, you can find on the website of the workshop online the list of the poster and the numbers. The numbers will correspond to the place. Thank you all.
Thank you.
So tomorrow morning we start at 9, but those who are presenting should come earlier in order to upload the presentations if they don't do it this evening, because they are not yet there.